On July 20th, 1969, one of the most phenomenal events made its way into the history books, when the Apollo 11 completed its historic mission to the moon. While the most brilliant minds helped to make sure that the Eagle had landed, computers also played a significant role. The guidance system that navigated the spacecraft was one of the earliest forms of modern computing. That same computer, the one that helped America's lunar dreams become a reality, took up the space of an entire room and had 1/10,000th the computing power of the thing that almost every one of you carry in your pockets today, a smartphone. Computer hardware and software have had such a dramatic evolution that what was once only used to power rockets now shapes the entire way our world functions. Think about your day. Did you grab a snack, turn on your TV, take a drive in your car? Computers were along for the ride, literally. Computers are everywhere. So here's the rundown. By the end of this course, you'll understand how computers work and get a grasp of the building blocks of IT. We're going to cover the basics of how computer hardware performs calculations, and we're going to actually build a computer from the ground up. We'll look at how operating systems control and interact with hardware. We'll take a look at the internet and get a better understanding of how computers talk to each other. We'll also spend time learning about how applications and programs tie all of this together and let humans interact with these systems. Finally, we'll cover important lessons on problem solving with computers and cover the communication skills that are so critical when interacting with others in IT. Whether you're looking for a job in the IT industry or you just want to learn how your laptop connects to the internet, understanding how computers work at every level can help you in your day-to-day life and in the workplace. But first, let's take a step way back to where it all began, even before the Apollo 11 mission touched down, so you can understand how and why we use computers today. Welcome to Course 1, Technical Support Fundamentals. My name is Kevin Limehouse, and I work as a support specialist for platforms billing DoubleClick at Google. Looking back, I can trace where my passion for IT began to an actual moment when I was 8 years old. My parents were about to throw away our old busted computer, but I managed to convince my mom to let me keep it. I remember the moment when I slowly started disassembling it. Kept digging deeper and deeper, unscrewing every little piece I can get my hands on, and I was hooked. By the time I was 12 or 13 years old, I became the de facto IT support for my entire family, and that's no small feat considering I have 11 aunts and uncles and over 35 cousins. My parents both grew up in very small rural towns in South Carolina. Growing up in the Jim Crow South through the mid-1950s and 1960s, they were taught at an early age that one of the better methods to get ahead was through education. This lesson was instilled in me and my sister, and I ended up going to university to study computer science. I graduated school right at the end of the 2007 and 2009 recession, but thankfully I secured a job at Google in IT support, where I work with users, solving their issues and supporting the IT inventory. And now I've been working in IT for 7 years. In my current role as a support specialist, I provide technical and billing support to Google sales teams, which involves everything from troubleshooting to creating forms or editing automation scripts. And now you know a little bit about me. Let's start from the beginning. What is information technology? Information technology has completely transformed your life in ways that you may not even realize. Thanks to IT, we can communicate massive amounts of information to people and organizations across the world in the blink of an eye. Computers power everything from calculators to medical equipment to complex satellite systems and the trading desk of Wall Street. They're powerful and invaluable tools that help people get their work done and enable us to connect with one another. So what exactly is information technology? IT is essentially the use of digital technology, like computers and the internet, to store and process data into useful information. The IT industry refers to the entire scope of all the jobs and resources that are related to computing technologies within society. And there are a lot of different types of jobs in this field, from network engineers who ensure computers can communicate with each other, to hardware technicians who replace and repair components, to desktop support personnel who make sure that end users can use their software properly. But IT isn't just about building computers and using the internet, it's really about the people. That's the heart and soul of IT support work. What good is technology or information if people can't use technology or make sense of the information? IT helps people solve meaningful problems by using technology, which is why you'll see its influences in education, medicine, journalism, construction, transportation, entertainment, or really any industry on the planet. IT is about changing the world through the ways we collaborate, share, and create together. IT has become such a vital tool in modern society that people and organizations who don't have access to IT are at a disadvantage. IT skills are becoming necessary for day-to-day living, like finding a job, getting an education, and looking up your health information. Maybe you're from a community where there wasn't any internet, or you couldn't afford a super fast computer and had to use one at your school or library instead. There are many social and economic reasons why some people have digital literacy skills and other people do not. This growing skills gap is known as the digital divide. People without digital literacy skills are falling behind, but people like you are the real solution to bridging that digital divide. Overcoming the digital divide not only involves confronting and understanding the combination of socioeconomic factors that shape our experience, but also helping others confront and understand those experiences. By getting into IT, you'll help serve those in your communities or organizations and maybe even inspire a new generation of IT pioneers. When I think about solving the digital divide, I can't help but think of all the opportunities and breakthroughs that folks from diverse backgrounds and perspectives in the industry can bring. By bringing more people of color, more women, more ethnically diverse people into the IT field, we're bound to see unique, new ideas and products that we haven't even begun to imagine. That benefits everybody. So what's the day-to-day work of someone in IT support like? Well, it varies a ton based on whether you're doing in-person or remote support and at a small business or a large enterprise company. And there's really no such thing as day-to-day work, since the puzzles and challenges are always new and interesting. But in general, an IT support specialist makes sure that an organization's technological equipment is running smoothly. This includes managing, installing, maintaining, troubleshooting, and configuring office and computing equipment. This program is designed to prepare you for an entry-level role in IT help desk support. You'll learn how to set up a user's desktop or workstation, how to install the computer applications that people use the most. You'll learn how to fix a problem or troubleshoot when something goes wrong, and how to put practices in place to prevent similar problems from happening again. Not only will you learn the technical aspects of troubleshooting a problem, you'll also learn how to communicate with users in order to best assist them. We'll also show you how to set up a network from scratch to connect to the internet, and teach you about how to implement security to make sure your systems are safe from hackers and other risks. For me, my favorite part of IT support is the problem-solving aspect. I love to exercise my creativity to spin up a solution to a user's issue. Being an IT generalist also gave me the flexibility to learn and practice so many different skills and eventually determine where I want to focus my career. Plus, when things go wrong or you fail at something in IT, you can take the feedback from those mistakes and be better equipped to tackle them the next time around. Using failure as a feedback is an important skill both in IT and in life. For me, that's why I was so attracted to the IT field. I love the process of problem solving and constantly stretching myself to learn and grow. There's also never been more opportunity to get into the IT industry than now. Not only is the field of IT incredibly diverse, but job prospects are also booming. It's projected that IT jobs in the US alone will grow 12% in the next decade. That's higher than the average for all other occupations. So what does this all mean? There are thousands of companies around the world searching for IT professionals like you. So the main gist is that IT is totally awesome and full of opportunity, and we're so excited that you're here. So let's dive right in. When you hear the word computer, maybe you think of something like a beefy gaming desktop with flashing lights, or maybe you think of a slim and sleek laptop. These fancy devices aren't what people had in mind when computers were first created. To put it simply, a computer is a device that stores and processes data by performing calculations. Before we had actual computer devices, the term computer was used to refer to someone who actually did the calculation. You're probably thinking that's crazy talk. My computer lets me check social media, browse the internet, design graphics. How can it possibly just perform calculations? Well, friends, in this course, we'll be learning how computer calculations are baked into applications, social media, games, etc., all the things that you use every day. But to kick things off, we'll learn about the journey computers took from the earliest known forms of computing into the devices that you know and love today. In the world of technology, and if I'm getting really philosophical in life, it is important to know where we've been in order to understand where we are and where we are going. Historical context can help you understand why things work the way they do today. Have you ever wondered why the alphabet isn't laid out in order on your keyboard? The keyboard layout that most of the world uses today is the QWERTY layout, distinguished by the Q, W, E, R, T, and Y keys in the top row of the keyboard. The most common letters that you type aren't found on the home row, where your fingers hit the most. But why? There are many stories that claim to answer this question. Some say it was developed to slow down typists so they wouldn't jam old mechanical typewriters. Others claim it was meant to resolve problems for telegraph operators. One thing is for sure, the keyboard layout that millions of people use today isn't the most effective one. Different keyboard layouts have even been created to try and make typing more efficient. Now that we're starting to live in a mobile-centric world with our smartphones, the landscape for keyboards may change completely. My typing fingers are crossed. In the technology industry, having a little context can go a long way to making sense of the concepts you'll encounter. By the end of this lesson, you'll be able to identify some of the most major advances in the early history of computers. Do you know what an abacus is? It looks like a wooden toy that a child would play with, but it's actually one of the earliest known computers. It was invented in 500 BC to count large numbers. While we have calculators like the old reliable TI-89s or the ones in our computers, the abacus is actually still used today. Over the centuries, humans built more advanced counting tools, but they still required a human to manually perform the calculations. The first major step forward was the invention of the mechanical calculator in the 17th century by Blaise Pascal. This device used a series of gears and levers to perform calculations for the user automatically. While it was limited to addition, subtraction, multiplication, and division for pretty small numbers, it paved the way for more complex machines. The fundamental operations of the mechanical calculator were later applied to the textile industry. Before we had streamlined manufacturing, looms were used to weave yarn into fabric. If you wanted design patterns on your fabric, that took an incredible amount of manual work. In the 1800s, a man by the name of Joseph Jacquard invented a programmable loom. These looms took a sequence of cards with holes in them. When the loom encountered a hole, it would hook the thread underneath it. If it didn't encounter a hole, the hook wouldn't thread anything. Eventually, this spun up a design pattern on the fabric. These cards were known as punch cards. And while Mr. Jacquard reinvented the textile industry, he probably didn't realize that his invention would shape the world of computing and the world itself today. Pretty epic, Mr. Jacquard, pretty epic. Let's fast forward a few decades and meet a man by the name of Charles Babbage. Babbage was a gifted engineer who developed a series of machines that are now known as the greatest breakthrough on our way to the modern computer. He built what was called a difference engine. It was a very sophisticated version of some of the mechanical calculators we were just talking about. It could perform fairly complicated mathematical operations, but not much else. Babbage's follow-up to the difference engine was a machine he called the analytical engine. He was inspired by Jacquard's use of punch cards to automatically perform calculations instead of manually entering them by hand. Babbage used punch cards in his analytical engine to allow people to predefine a series of calculations they wanted to perform. As impressive as this achievement was, the analytical engine was still just a very advanced mechanical calculator. It took the powerful insights of a mathematician named Ada Lovelace to realize the true potential of the analytical engine. She was the first person to recognize that the machine could be used for more than pure calculations. She developed the first algorithm for the engine. It was the very first example of computer programming. An algorithm is just a series of steps that solve specific problems. Because of Lovelace's discovery that algorithms could be programmed into the analytical engine, it became the very first general-purpose computing machine in history. And a great example that women have had some of the most valuable minds in technology since the 1800s. We've covered a lot of ground already, learning about how primitive counting devices like the abacus evolved into huge, complex devices like the analytical engine, proof that there was life before social media. In the next video, we'll learn about how these mechanical machines made the leap into modern computing. Welcome back. In this video, we'll be learning how huge devices like the analytical engine shrunk into the computing devices that we use today. The development of computing has been steadily growing since the invention of the analytical engine, but didn't make a huge leap forward until World War II. Back then, research into computing was super expensive, electronic components were large, and you needed lots of them to compute anything of value. This also meant that computers took up a ton of space, and many efforts were underfunded and unable to make headway. But when the war broke out, governments started pouring money and resources into computing research. They wanted to help develop technologies that would give them advantages over other countries. Lots of efforts were spun up and advancements were made in fields like cryptography. Cryptography is the art of writing and solving codes. During the war, computers were used to process secret messages from enemies faster than a human could ever hope to do. Today, the role cryptography plays in secure communication is a critical part of computer security, which you'll learn more about in a later course. For now, let's look at how computers started to make a dramatic impact on society. First up is Alan Turing, an English mathematician and now famous computer scientist. He helped develop the top-secret Enigma machine, which helped Allied forces decode Axis messages during World War II. The Enigma machine is just one of the examples of how governments started to recognize the potential of computation. After the war, companies like IBM, Hewlett-Packard, and others were advancing their technologies into the academic, business, and government realms. Lots of technological advancements in computing were made in the 20th century, thanks to direct interest from governments, scientists, and companies left over from World War II. These organizations invented new methods to store data in computers, which fueled the growth of computational power. Consider this: until the 1950s, punch cards were a popular way to store data. Operators would have decks of ordered punch cards that were used for data processing. If they dropped the deck by accident and the cards got out of order, it was almost impossible to get them sorted again. There were obviously some limitations to punch cards, but thanks to new technological innovations like magnetic tape and its counterparts, people began to store more data on more reliable media. A magnetic tape worked by magnetizing data onto a tape. Back in the 1970s and 80s, people used to listen to music on vinyl records or cassette tapes. These relics are examples of how magnetic tapes can store information and run that information from a machine. This left stacks and stacks of punch cards to collect dust while their new magnetic tape counterparts began to revolutionize the industry. I wasn't joking when I said early computers took up a lot of space. They had huge machines to read data and racks of vacuum tubes that helped move that data. Vacuum tubes controlled the electricity voltages in all sorts of electronic equipment like televisions and radios, but these specific vacuum tubes were bulky and broke all the time. Imagine what the work of an IT support specialist was like in those early days of computing. The job description might have included crawling around inside huge machines filled with dust and creepy crawly things, while replacing vacuum tubes and swapping out those punch cards. In those days, doing some debugging might have taken on a more literal meaning. Renowned computer scientist Admiral Grace Hopper had a favorite story involving some engineers working on the Harvard Mark II computer. They were trying to figure out the source of the problems in a relay. After doing some investigating, they discovered the source of their trouble was a moth, a literal bug in the computer. The ENIAC was one of the earliest forms of general-purpose computers. It was a wall-to-wall convolution of massive electronic components and wires. It had 17,000 vacuum tubes and took up about 1,800 square feet of floor space. Imagine if you had to work with that scale of equipment today. I wouldn't want to share an office with 1,800 square feet of machinery. Eventually, the industry started using transistors to control electricity voltages. This is now a fundamental component of all electronic devices. Transistors perform almost the same functions as vacuum tubes, but they are more compact and more efficient. You can easily have billions of transistors in a small computer chip today. Throughout the decades, more and more advancements were made. The very first compiler was invented by Admiral Grace Hopper. Compilers made it possible to translate human language via a programming language into machine code. In case you didn't totally catch that, we'll talk more about compilers later in this course. The big takeaway is that this advancement was a huge milestone in computing that led to where we are today. Now, learning programming languages is accessible for almost anyone anywhere. We no longer have to learn how to write machine code in ones and zeros. You'll get to see these languages in action in future lessons where you'll write some code yourself. Side note, if the thought of that scares you, don't worry. We'll help you every step of the way. But for now, let's get back to the evolution of computers. Eventually, the industry gave way to the first hard disk drives and microprocessors. Then, programming language started becoming the predominant way for engineers to develop computer software. Computers were getting smaller and smaller, thanks to advancements in electronic components. Instead of filling up entire rooms like ENIAC, they were getting small enough to fit on tabletops. The Xerox Alto was the first computer that resembled the computers we're familiar with now. It was also the first computer to implement a graphical user interface that used icons, a mouse, and a window. Some of you may remember that the sheer size and cost of historical computers made it almost impossible for an average family to own one. Instead, they were usually found in military and university research facilities. When companies like Xerox started building machines at a relatively affordable price and at a smaller form factor, the consumer age of computing began. Then in the 1970s, a young engineer named Steve Wozniak invented the Apple I, a single-board computer meant for hobbyists. With his friend Steve Jobs, they created a company called Apple Computer. Their follow-up to the Apple I, the Apple II, was ready for the average consumer to use. The Apple II was a phenomenal success, selling for nearly 2 decades and giving a new generation of people access to personal computers. For the first time, computers became affordable for the middle class and helped bring computing technology into both the home and office. In the 1980s, IBM introduced its personal computer. It was released with a primitive version of an operating system called MS-DOS, or Microsoft Disk Operating System. Side note, modern operating systems don't just have text anymore. They have beautiful icons, words, and images like what we see on our smartphones. It's incredible how far we've come from the first operating system to the operating systems we use today. Back to IBM's PC. It was widely adopted and made more accessible to consumers thanks to a partnership with Microsoft. Microsoft, founded by Bill Gates, eventually created Microsoft Windows. For decades, it was the preferred operating system in the workplace and dominated the computing industry because it could be run on any compatible hardware. With more computers in the workplace, the dependence on IT rose, and so did the demand for skilled workers who could support that technology. Not only were personal computers entering the household for the first time, but a new type of computing was emerging: video games. During the 1970s and 80s, coin-operated entertainment machines called arcades became more and more popular. A company called Atari developed one of the first coin-operated arcade games in 1972 called Pong. Pong was such a sensation that people were standing in lines at bars and rec centers for hours at a time to play. Entertainment computers like Pong launched the video game era. Eventually, Atari went on to launch the Video Computer System, which helped bring personal video consoles into the home. Video games have contributed to the evolution of computers in a very real way. Tell that to the next person who dismisses them as a toy. Video games show people that computers didn't always have to be all work and no play. They were a great source of entertainment too. This was an important milestone for the computing industry, since at that time, computers were primarily used in the workplace or at research institutions. With huge players in the market like Apple, Macintosh, and Microsoft Windows taking over the operating system space, a programmer by the name of Richard Stallman started developing a free Unix-like operating system. Unix was an operating system developed by Ken Thompson and Dennis Ritchie, but it wasn't cheap and wasn't available to everyone. Stallman created an OS that he called GNU. It was meant to be free to use with similar functionality to Unix. Unlike Windows or Macintosh, GNU wasn't owned by a single company. Its code was open source, which meant that anyone could modify and share it. GNU didn't evolve into a full operating system, but it set a foundation for the formation of one of the largest open source operating systems, Linux, which was created by Linus Torvalds. We'll get into the technical details of Linux later in this course, but just know that it's a major player in today's operating systems. As an IT support specialist, it is very likely that you'll work with an open source software. You might already be using one like the internet browser Mozilla Firefox. By the early 90s, computers started getting even smaller. Then a real game changer made its way into the scene: PDAs, or personal digital assistants, which allows computing to go mobile. These mobile devices included portable media players, word processors, email clients, internet browsers, and more, all in one handy handheld device. In the late 1990s, Nokia introduced the PDA with mobile phone functionality. This ignited an industry of pocketable computers, or as we know them today, smartphones. In mere decades, we went from having computers that weighed tons and took up entire rooms to having powerful computers that fit in our pockets. It's almost unbelievable. And it's just the beginning. If you're stepping into the IT industry, it's essential that you understand how to support the growing need of this ever-changing technology. Computer support 50 years ago consisted of changing vacuum tubes and stacking punch cards, things that no longer exist in today's IT world. While computers evolved in both complexity and prevalence, so did knowledge required to support and maintain them. In 10 years, IT support could require working through virtual reality lenses. You never know. Who knows what the future holds, but right now, it is an exciting time to be at the forefront of this industry. Now that we've run down where computers came from and how they've evolved over the decades, let's get a better grasp on how computers actually work. Remember when I said that a computer is a device that stores and processes data by performing calculations? Whether you're creating an artificial intelligence that can beat humans at chess, or something more simple like running a video game, the more computing power you have access to, the more you can accomplish. By the end of this lesson, you'll understand what a computer calculates and how. Let's look at this simple math problem. 0 plus 1 equals what? It only takes a moment to come up with the answer 1, but imagine that you needed to do 100 calculations that were this simple. You could do it, and if you were careful, you might not make any mistakes. But what if you needed to do 1,000 of these calculations? How about 1,000,000? How about 1,000,000,000? This is exactly what a computer does. A computer simply compares ones and zeros, but millions or billions of times per second. Wowza. The communication that a computer uses is referred to as binary system, also known as base 2 numeral system. This means that it only talks in ones and zeros. You may be thinking, okay, my computer only talks in ones and zeros, how do I communicate with it? Think of it like this. We use the letters of the alphabet to form words, and we give those words meaning. We use them to create sentences, paragraphs, and whole stories. The same thing applies to binary, except instead of A, B, C, and so on, we only have 0 and 1 to create words that we give meaning to. In computing terms, we group binary into 8 numbers, or bits. Technically, a bit is a binary digit. Historically, we use 8 bits because in the early days of computing, hardware utilized the base 2 numeral system to move bits around. 2 to the 8th numbers offered us a large enough range of values to do the computing we needed. Back then, any number of bits was used, but eventually the grouping of 8 bits became the industry standard that we use today. You should know that a group of 8 bits is referred to as a byte. So a byte of zeros and ones could look like 100111011. Each byte can store one character, and we can have 256 possible values thanks to the base 2 system, 2 to the 8th. In computer talk, this byte can mean something like the letter C. And this is how computer language is born. Let's make a quick table to translate something a computer might see into something we'd be able to recognize. What does the following translate to? Did you get hello? Pretty cool, right? By using binary, we can have unlimited communication with our computer. Everything you see on your computer right now, whether it's a video, an image, text, or anything else, is nothing more than a 1 or a 0. It is important that you understand how binary works. It is the basis for everything else we'll do in this course, so make sure you understand the concept before moving on. Remember from the earlier video that a byte can store only zeros and ones. That means we can have 256 possible values. By the end of this video, you'll learn how we can represent the words, numbers, emojis, and more we see on our screens from only these 256 possible values. It's all thanks to character encoding. Character encoding is used to assign our binary values to characters so that we as humans can read them. We definitely wouldn't want to see all the text in our emails and web pages rendered in complex sequences of zeros and ones. This is where character encodings come in handy. You can think of character encoding as a dictionary. It's a way for your computers to look up which human character should be represented by a given binary value. The oldest character encoding standard used is ASCII. It represents the English alphabet, digits, and punctuation marks. The first character in the ASCII to binary table, a lowercase a, maps to 011000001 in binary. This is done for all the characters you can find in the English alphabet, as well as numbers and some special symbols. The great thing with ASCII was that we only needed to use 127 values out of our possible 256. It lasted for a very long time, but eventually it wasn't enough. Other character encoding standards were created to represent different languages, different amounts of characters, and more. Eventually, they would require more than 256 values we were allowed to have. Then came UTF-8, the most prevalent encoding standard used today. Along with having the same ASCII table, it also lets us use a variable number of bytes. What do I mean by that? Think of any emoji. It's not possible to make emojis with a single byte since we can only store one character in a byte. Instead, UTF-8 allows us to store a character in more than one byte, which means endless emoji fun. UTF-8 is built off the Unicode standard. We won't go into much detail, but the Unicode standard helps us represent character encoding in a consistent manner. Now that we've been able to represent letters, numbers, punctuation marks, and even emojis, how do we represent color? Well, there are all kinds of color models. For now, let's stick to a basic one that's used in a lot of computers, RGB, or red, green, and blue model. Just like the actual colors, if you mix a combination of any of these, you'll be able to get the full range of colors. In Computerland, we use 3 characters for the RGB model. Each character represents a shade of the color, and that then changes the color of the pixel you see on your screen. With just 8 combinations of zeros and ones, we're able to represent everything that you see on your computer, from a simple letter A to the very video that you're watching right now on the Coursera website. Very cool. In the next video, we'll discuss how we actually generate the zeros and ones. You might be wondering how our computers get these ones and zeros. It's a great question. Imagine we have a light bulb and a switch that turns the state of the light on or off. If we turn the light on, we can denote that state as 1. If the light bulb is off, we can represent the state as 0. Now imagine 8 light bulbs and switches. That represents 8 bits with a state of 0 or 1. Let's backtrack to the punch cards that were used in Jacquard's loom. Remember that the loom used cards with holes in them. When the loom would reach a hole, it would hook the thread underneath, meaning that the loom was on. If there wasn't a hole, it would not hook the thread, so it was off. This is a foundational binary concept. By utilizing the 2 states of on or off, Jacquard was able to weave intricate patterns into fabric with his looms. Then the industry started refining the punch cards a little more. If there was a hole, the computer would read 1. If there wasn't a hole, it would read 0. Then, by just translating the combination of zeros and ones, our computer could calculate any possible amount of numbers. Binary in today's computer isn't done by reading holes. It uses electricity via transistors, allowing electrical signals to pass through. If there's an electric voltage, we would denote it as 1. If there isn't, we would denote it by 0. But just having transistors isn't enough for our computer to be able to do complex tasks. Imagine if you had 2 light switches on opposite ends of a room, each controlling a light in the room. What if, when you went to turn on the light with one switch, the other switch wouldn't turn off? That would be a very poorly designed room. Both switches should either turn the light on or off, depending on the state of the light. Fortunately, we have something known as logic gates. Logic gates allow our transistors to do more complex tasks like decide where to send electrical signals depending on logical conditions. There are lots of different types of logic gates, but we won't discuss them in detail here. If you're curious about the role that transistors and logic gates play in modern circuitry, you can read more about it in the supplementary reading. Now we know how our computer gets its ones and zeros to calculate into meaningful instructions. Later in this course, we'll be able to talk about how we're able to turn human readable instructions into zeros and ones that our computer understands through compilers. That's one of the very basic building blocks of programming that's led to the creation of our favorite social media sites, video games, and just about everything else. And I'm super excited to teach you how to count in binary. That's up next. Binary is the fundamental communication block of computers, but it's used to represent more than just text and images. It's used in many aspects of computing like computer networking, which you'll learn about in a later course. It's important that you understand how computers count in binary. We've shown you simple lookup tables that you can use like the ASCII to binary table, But as an IT support specialist, whether you're working on networking or security, you'll need to know how binary works. So let's get started. You'll probably need a trusty pen and paper, a calculator, and some good old-fashioned brain power to help you in this video. The binary system is how our computers count, using ones and zeros. But humans don't count like that. When you were a child, you may have counted using 10 fingers on your hand. That innate counting system is called the decimal form, or base 10 system. In the decimal system, there are 10 possible numbers you can use, ranging from 0 to 9. When we count binary, which only uses 0 and 1, we convert it to a system that we can understand, decimal. 330, 250, 240, 4 million. They're all decimal numbers. We use the decimal system to help us figure out what bits our computer can use. We can represent any number in existence just by using bits. That's right, we can represent this number just using ones and zeros. So how does that work? Let's consider these numbers: 128, 64, 32, 16, 8, 4, 2, and 1. What patterns do you see? Hopefully you'll see that each number is a double of the previous number going right to left. What happens if you add them all up? You get 255. That's kind of weird. I thought we could have 256 values for a byte. Well, we do. The 0 is counted as a value, so the maximum decimal number you can have is 255. What do you think the number is represented here? See where the ones and the zeros are represented? Remember, if our computer sees a 1, then the value is on. If it sees a 0, then the value is off. If you add these numbers up, you'll get a decimal value. If you guess 10, then you're right. Good job. If you didn't get it, that's okay too. Take another look. The 2 and 8 are on, and if we add them up, we get 10. Let's look at our ASCII to binary table again. The letter H in binary is 011010000. Now let's look at an ASCII to decimal table. The letter H in decimal is 104. Now let's try our conversion chart again. 64 plus 32 plus 8 equals 104. Look at that. The math checks out. Now we're cooking. Wow, we've gone over all the essentials of the basic building blocks of computing and machine language. Next, you're going to learn how we build on top of this layer of computing to perform the task you'll do day to day. When we interact with our computers, we use our mouse, keyboard, or even a touchscreen. We don't tell it the actual zeros and ones it needs to understand something. But wait, we actually do. We just don't ever have to worry about it. We use the concept of abstraction to take a relatively complex system and simplify it for our use. You use abstraction every day in the real world, and you may not even know it. If you've ever driven a car, you don't need to know how to operate the transmission or the engine directly. There's a steering wheel, some pedals, maybe a gear stick. If you buy a car from a different manufacturer, you operate it in pretty much the same way, even though the stuff under the hood might be completely different. This is the essence of abstraction. Abstraction hides complexity by providing a common interface: the steering wheel, pedals, gear stick, and gauges in our car example. The same thing happens in our computer. We don't need to know how it works underneath the hood. We have a mouse and a keyboard we can use to interact with it. Thanks to abstraction, the average computer user doesn't have to worry about the technical details. We'll use this under the hood metaphor throughout the program to describe the area that contains the underlying implementation of a technology. In computing, we use abstraction to make a very complex problem, like how to make computers work, easier to think about. We do that by breaking it apart into simpler ideas that describe single concepts or individual jobs that need to be done, and then stack them in layers. This concept of abstraction will be used throughout this entire course. It's a fundamental concept in the computing world. Another simple example of abstraction in an IT role that you might see a lot is an error message. We don't have to dig through someone else's code and find a bug. This has been abstracted out for us already in the form of an error message. A simple error message like "found not found" actually tells us a lot of information and saves us time to figure out a solution. Can you imagine if instead of abstracting an error message, our computer did nothing and we had no clue where to start looking for answers? Abstraction helps us in many ways that we don't even realize. In the last video, I mentioned that people don't need to understand how a computer works for them to use it because abstraction makes things simpler for us. That's technically true, but since you're stepping into the world of IT, you do need to understand all the layers of a computer and how they work. It's essential that you understand how the different pieces interact so you can resolve any issue that may arise. For the rest of this course, we'll deep dive into the layers of computer architecture and learn all the parts that make up a computer. A computer can be cut into 4 main layers: hardware, operating system, software, and users. The hardware layer is made up of the physical components of a computer. These are objects you can physically hold in your hand: laptops, phones, monitors, keyboards. You get the idea. In the next lesson, you'll learn all of the components of a computer and how they work. You'll even be able to build your own computer by the end of this module. The operating system allows hardware to communicate with the system. Hardware is created by many different manufacturers. The operating system allows them to be used with our system regardless of where it came from. In the next few lessons, you'll learn about the major operating systems that we use today, and you'll be able to understand all of the underlying components that make up an operating system. By the end of these lessons, you'll have a strong grasp on the major components of any operating system like Android or Windows, and use that knowledge to navigate any operating system. The software layer is how we as humans interact with our computers. When you use a computer, you're given a vast amount of software that you interact with, whether it's a mobile app, a web browser, a word processor, or the operating system itself. Later in this course, we'll learn how software is installed on our systems and how we interact with different types of software. The last layer may not seem like it's part of the system, but it's an essential layer of the computer architecture: the user. The user interacts with the computer, and she can do more than that. She can operate, maintain, and even program the computer. The user layer is one of the most important layers we'll learn about. When you step into the field of IT, you may have your hands full with the technical aspects, but the most important part of IT is the human element. While we work with computers every day, it is the user interaction that makes up most of our job, from responding to user emails to fixing their computers. By the end of the course, you'll also learn how to apply your knowledge of how a computer works to fix real-world issues that can sometimes seem random and obscure. We'll do this by learning how to utilize problem-solving tactics to identify issues and solutions. There's a lot ahead. The next instructor you're going to meet is a friend of mine, Devin Sreetharan. And I know there's no better person to teach you about hardware. He'll even show you how to build a computer from its component parts. Pretty cool. But before you get to building that computer, we got a quiz coming up for you on binary counting.
Let's face it, computers are everywhere. You come into contact with them at home, work, the airport, the grocery store. You're using some type of computer to take this course. You know what? There's probably one in your pocket right now. While computers are complex and can seem daunting to learn, they ultimately just calculate, process, and store data. In this lesson, we're going to take a peek at what's inside of a computer. We'll spend the next few lessons explaining how each of these components work, but for now, let's check out a typical desktop setup. Desktops are just computers that can fit on or under our desks. So here we have a monitor, a keyboard, a mouse, and a desktop. Sometimes we might even add a webcam, speakers, or a printer setup. We'll call these physical components hardware. Let's take a look at the back of the computer. You can see common connectors here, the power outlet here, and the common ports here. Ports are connection points that we can connect devices to that extend the functionality of our computer. We'll go into detail about the ports you see here in a later lesson, but here's a quick rundown. We have a port here to connect to a monitor, and a few ports here to plug your keyboard and mouse. There's another important one here for our network connection. With just these ports, we're able to have the basic functionality to browse the web and much more. Things look pretty similar on a laptop. Here are some of the same ports, a built-in monitor, and a keyboard. There are also physical components inside the laptop case that are hidden for portability. Once you figure out how one computer works, you can figure out how any other computer works. Okay, this is my favorite part. Let's open up this desktop and take a deeper look. Let me first clean up my desk. Get ready for it. Whoa, it looks pretty complicated, but that's okay. We'll take you through it. Let's start with a quick tool. Then we'll dive deeper into each of these parts in the next lesson. Right here, this component is the CPU, or Central Processing Unit, which is covered by this heatsink. You can think of the CPU as the brain of our computer. The CPU does all the calculations and data processing. It communicates pretty heavily with this component right here, RAM, or random access memory. RAM is our computer's short-term memory. We use this component when we want to store data temporarily. Like, let's say you're typing something into a chat or a piece of text in a word processor. This information is stored in the RAM. Don't worry, we'll cram in more details on RAM in a later lesson. When we want to store anything in long-term memory, we use this component here, the hard drive. The hard drive holds all our data, which can include music, pictures, applications. Let me show you something else interesting. Have you noticed this large slab here? This is our motherboard. It holds everything in place and lets our components communicate with each other. It's the foundation of our computer. You can think of the motherboard as the body or circuitry system of the computer that connects all the pieces together. The last component we'll talk about is our power supply, which converts electricity from our wall outlet onto a format that our computer can use. You know what's interesting? All these components make up most computers, even a mobile phone. While it might look very different from your laptop, a mobile phone just uses a smaller version of the hardware that we saw in the desktop and laptop today. So now that we've covered the basic anatomy of a computer, we'll go over each of these components in depth in the next few lessons. Understanding how computer hardware works is a really helpful skill set in IT support. Since an IT department maintains the hardware that a company uses, a solid understanding of these computer internals will come in handy when troubleshooting hardware-related problems. And taking things apart to see how they work is just super fun. Before we get our hands dirty with learning how to build a computer, let's talk theory first. In an earlier lesson, we talked about binary and how computers perform calculations. Remember that our computer can only communicate in binary using ones and zeros. Our computers speak in machine language, but we, of course, speak in human languages like English, Spanish, Mandarin, Hindi. You get the idea. If we want to communicate with our machines, we have to have some sort of translation dictionary. Just like if I wanted to say something in Spanish, I'd look it up in an English to Spanish dictionary. Well, our computers have a built-in translation book. In this lesson, we'll dive deeper into how our computer translates the information we give it into instructions that it understands. Right now, you're probably using a web browser, a music player, text editor, or something else on your computer. We interact with these applications on a daily basis. They're referred to as programs. Programs are basically instructions that tell the computer what to do. We typically store programs on durable media like hard drives. You can think of programs like cooking recipes. We'll keep these recipes all stored together in a cookbook, just like apps stored in a hard drive. Now, we want to make a ton of food, so we hire a chef to follow our recipes and whip up something good. The faster our chef works, the more food she'll prepare. The chef is our CPU. She processes the recipes we send her and makes the food. Our chef works super fast, so fast that she can cook faster than she can read. So, we take copy of the recipes and put them into RAM. Remember that RAM is our computer's short-term memory. It stores information in a location our CPU can access it faster than it could with our hard drive. Now we can give our chef 1 or 2 recipes at a time instead of reciting the entire cookbook to her. Okay, now let's say I want to make a peanut butter and jelly sandwich. I see a pretty good recipe and send it to our chef to make. Remember that our chef needs these instructions quickly, so I don't send her the entire recipe, I send her one line at a time. 1. Get 2 slices of bread. 2. Put peanut butter on one slice. 3. Put jelly on another slice. 4. Combine the 2 slices of bread. Now, let me throw one more thing at you. Our chef can only communicate with us in ones and zeros. So instead of sending something readable, like the recipe for a peanut butter and jelly sandwich, we have to send her something like this. In reality, this process is a little more complicated. Our CPU is constantly taking instructions and executing them. These instructions are written in binary, but how do they travel around the computer? In our computer, we have something called the External Data Bus, or EDB. It's nothing like a bus at all. It's a row of wires that interconnect the parts of our computer, kind of like the veins in our body. When you send a voltage to one of the wires, we say the state of the wire is on, or represented by a 1. If there's no voltage, then we say that the state is off, represented by a 0. This is how we send around our ones and zeros. Sound familiar? In the last lesson, we talked about how transistors help us to send voltages. Now, we know how our bits physically travel around the computer. The EDB comes in different sizes: 8-bit, 16-bit, 32, even 64. Can you imagine if you had 64 wires going? You can move around a lot more data. Right now, we're just going to stick with using an EDB with 8 bits in our examples, sending 1 byte at a time. Okay, so now our CPU is receiving a byte and it needs to get to work. Inside the CPU, there are components known as registers. They let us store the data that our CPU works with. If, for example, our CPU wanted to add 2 numbers, one number would be stored in register A. Another number would be stored in register B. The result of those 2 numbers would be stored in register C. Imagine, the register is one of our chef's work tables. Since she has a place to work, she can start to cook. To do so, she uses a translation book to translate her binary into tasks that she can perform. Let's jump back for a second. Remember that our programs are copied into RAM for the CPU to read. RAM is memory that's randomly accessed, allowing our CPU to read from any part of RAM as quickly as any other part. We don't actually send data from RAM over the EDB. There would be way too much stuff. RAM can hold millions, even billions of rows of data. Despite our sandwich example, most of our recipes aren't simple at all. They can be thousands of lines long. We want to process them and we don't actually go in any particular order. Since we can only send one line of data through the EDB at a time, we need the help of another component, the memory controller chip, or MCC. The MCC is a bridge between the CPU and the RAM. You can think of it like a nerve in your brain connecting to your memories. The CPU talks to the MCC and says, hey, I need the instructions for step number 3 of this recipe. The MCC finds the instructions for step number 3 in RAM, grabs the data, and sends it through the EDB. There's another bus that's nothing like a bus involved in the process called the address bus. It connects the CPU to the MCC and sends over the location of the data, but not the data itself. Then the MCC takes the address and looks for the data, and then data is then sent over the EDB. Believe it or not, RAM isn't the fastest way we can get more data to our CPU for processing. The CPU also uses something known as cache. Cache is smaller than RAM, but it lets us store data that we use often and lets us quickly reference it. Think of RAM like a refrigerator full of food. It's easy to get into, but it takes time to get something out. On the flip side of that, cache is like the stuff we have in our pockets. It's used to store recently or frequently accessed data. There are 3 different cache levels in a CPU: L1, L2, and L3. L1 is the smallest and fastest cache. If you're interested in learning more about this, you can check out the supplemental reading I've included right after this video. So now we understand how our RAM interacts with our CPU. But how does our CPU know when a set of instructions ends and a new one begins? Our CPU has an internal clock that keeps its operations in sync. It connects to a special wire called a clock wire. When you send or receive data, it sends a voltage to that clock wire to let the CPU know it can start doing calculations. Think of our clock wires as the ticking of a clock. For every tick, the CPU does one cycle of operations. When you send a voltage to the clock wire, it's referred to as a clock cycle. If you have lots of data you need to process in a command, you'll need to run lots of clock cycles. Have you ever seen a CPU in the store and it has something labeled 3.4 GHz? This number refers to the clock speed of the CPU, which is the maximum number of clock cycles that it can handle in a certain time period. 3.40 GHz is 3.4 billion cycles per second. That's super fast. But just because it can run at this speed doesn't mean it does. It just means that it can't exceed this number. Still, that number doesn't stop some people from trying. There's a way you can exceed the number of clock cycles on your CPU on almost any device. It's referred to as overclocking, and it increases the rate of your CPU clock cycles in order to perform more tasks. This is commonly used to increase the performance in low-end CPUs. Let's say you're a gamer and you want to have better graphics and less lag while playing. You might want to overclock your CPU when you play the game. But there are cons to doing this, like potentially overheating your CPU. You can read more about overclocking in the next supplementary reading. If someone asked you, calculate the square root of 5,439,493, would you do the math by hand? Unless you really love tedious math problems, you'd probably use a calculator. What about binary? Well, you probably wouldn't calculate binary by hand either. There's actually a very powerful calculator right inside of your computer that processes binary for us. We've already discussed this in calculator in detail. Do you know what it is? It's our CPU, the brain of our computer. In this video, we'll cover the more practical aspects of the CPU. Remember that translation book that I talked about in an earlier lesson? The CPU uses this to translate and perform functions on our data. This translation book is called an instruction set, which is literally just a list of instructions that our CPU is able to run. Functions like adding, subtracting, copying data are all instructions that our CPU can carry out. Every single program on your computer, while extremely complex, is broken down into very small and simple instructions found in our instruction set. Instruction sets are hard-coded into our CPU, so different CPU manufacturers may use different instruction sets, but they generally perform the same functions. It's like how car manufacturers build their engines differently, but they all get the same job done. You probably work with computer hardware as an IT support specialist, replacing failed hard disks, upgrading RAM modules, and installing video cards. So you need to be aware of what's out there. You've probably heard of a few popular CPU manufacturers or chipsets, like Intel, AMD, and Qualcomm. These CPU manufacturers use different product names to differentiate their processors, like Intel Core i7, AMD Athlon, Snapdragon 810, Apple A8, and more. Now when you hear these terms, you'll know what they mean. Each of these CPU manufacturers have their strengths and weaknesses. If you are interested in learning more about why some CPUs are more popular than others, you can check out the next supplemental reading. When you select your CPU, you'll need to make sure it's compatible with your motherboard, the circuit board that connects all your components together. Heads up, you can't just buy a bunch of parts and expect them to work together. There are different ways CPUs fit on motherboards using different sockets. Your CPU might have lots of tiny pins that either stick out or have contact points that look like dots. Depending on your motherboard, you'll need to make sure these CPUs fit correctly in the socket. There are currently two major types of CPU sockets: land grid array, also known as LGA, and pin grid array, also known as PGA. In an LGA socket like this one, there are pins that stick out of the motherboard. The socket size may vary, so always make sure your CPU and socket are compatible beforehand. When you purchase a CPU or motherboard, it'll tell you right on the box what type of socket it has. Make sure your CPU and motherboard socket also both match. If it's not listed on the box, you can go to the manufacturer's website, where it usually lists what types of CPUs are compatible with the motherboard. The other type of socket is the PGA socket, where the pins are located on the processor itself. When we install our CPU, we need to do a few things to it to keep it cool. Since it does a lot of work, it's prone to overheating. we have to make sure to include a heatsink too, which takes the heat from our CPU and dissipates it through a fan or another medium. There's one last thing I want to call out about CPUs. If you purchase a CPU, you'll see that it has either a 32-bit or 64-bit architecture. What does that mean? Well, we know we can process 8 bits in binary. Now, imagine how we can process with 32 or even 64 bits. CPUs that have 32-bit or 64-bit architecture are just specifying how much data they can efficiently handle. You can read more about the differences between 32-bit and 64-bit architecture in the next reading. For now, the main takeaway is that the CPU is one of the most important parts of a computer, so we have to make sure it's compatible with all other components and can perform well for our computing needs. Let's talk about RAM, our computer's short-term memory. We use RAM to store data that we want to access quickly. This data changes all the time, so it isn't permanent. Almost all RAM is volatile, which means that once we power off our machines, the data stored in RAM is cleared. Remember that our computer is comprised of programs. To run a program, we need to make a copy of it in RAM so our CPU can process it. When you see a new phone or laptop that says it has 16 gig of RAM, that means it can run up to 16 gigs of programs, meaning you can run lots of programs at the same time. When you type in a document, you're using RAM. If you've ever had the misfortune of working on an important presentation or paper and losing power, you know the feeling you get when all of the work you've done is lost. It's a total bummer. This happens to anything with RAM, even video games. Have you ever gone on a long campaign without saving? Then right as you get to a save point, the power goes off on the console and all the progress you've made is lost forever? It's no fun at all. You spend the next hour or so deciding whether or not just to rage quit the game completely and start all over from scratch. Not that this happened to me or anything, that was just a friend. Anyway, all of this happens because RAM clears its data when powered off. There are lots of types of RAM, and the one that's commonly found in computers is DRAM, or Dynamic Random Access Memory. When a 1 or a 0 is sent to DRAM, it stores each bit in a microscopic capacitor. This is either charged or discharged, represented by 1 or a 0. These semiconductors are put into chips that are on the RAM and store our data. There are also different types of memory sticks that DRAM chips can be put on. The more modern DIMM sticks, which usually stands for Dual Inline Memory Module, have different sizes of pins on them. I should call out, we don't really buy RAM based on the number of DRAM chips they have. They're labeled by the capacity of RAM on a stick, like an 8 gig stick of RAM. After DRAM was created, RAM manufacturers built something called SDRAM, which stands for Synchronous DRAM. This type of RAM is synchronized to our system's clock speed, allowing quicker processing of data. In today's system, we use another type of RAM called Double Data Rate SDRAM, or DDR SDRAM for short. Most people refer to this RAM as DDR, even shorter. There are lots of iterations of DDR, from DDR1, DDR2, DDR3, and now DDR4. DDR is faster, takes up less power, and has a larger capacity than earlier SDRAM versions. The latest version, DDR4, is the fastest type of short-term memory currently available for your computer. And faster RAM means that programs can be run faster and that more programs can run at the same time. Keep in mind that any RAM sticks you use need a compatible motherboard, where the different number of pins align with the motherboard RAM slots. Just like with the CPU, make sure that your motherboard is compatible with any RAM sticks that you buy. Up next, we'll take a deep dive into motherboards. The motherboard, the foundation that holds our computer together. It lets us expand our computer's functionality by adding expansion cards. It routes power from the power supply, and it allows the different parts of the computer to communicate with each other. In short, it's a total boss. Every motherboard has a few key characteristics. First is the chipset. which decides how components talk to each other on our machine. The chipset on motherboards is made up of two chips. One is called the North Bridge that interconnects stuff like RAM and video cards. The other chip is the South Bridge, which maintains our I/O or input-output controllers, like hard drives and USB devices that input and output data. In some modern CPUs, the North Bridge has been directly integrated into the CPU, so there isn't a separate North Bridge chipset. The chipset is a key component of our motherboard that allows us to manage data between our CPU, RAM, and peripherals. Peripherals are the external devices we connect to our computer, like a mouse, keyboard, and a monitor. You will learn more about peripherals in an upcoming lesson. In addition to the chipsets, motherboards have another key characteristic, which allows the use of expansion slots. Expansion slots also give us the ability to increase the functionality of our computer. If you wanted to upgrade your graphics card, you could purchase one and just install it on your motherboard through the expansion slot. The standard for an expansion bus today is the PCI Express, or Peripheral Component Interconnect Express. A PCIe bus looks like a slot on the motherboard, and a PCIe base expansion card looks like a smaller circuit board. The last component of motherboards that we'll discuss is form factor. There are different sizes of motherboards that are available today. These sizes, or form factors, determine the amount of stuff we can put in it and the amount of space we'll have. The most common form factor for motherboards is ATX, which stands for Advanced Technology Extended. ATX actually comes in different sizes too. In desktops, you'll commonly see full-sized ATXs. If you don't want to use an ATX form factor, you could use an ITX, or Information Technology Extended form factor. These are much smaller than ATX boards. For example, the Intel NUC uses a variation of the ITX board, which comes in 3 board sizes: Mini ITX, Nano ITX, and Pico ITX. When building your computer, you will need to keep in mind what type of form factor you want. Do you want to build something small that can't handle as much workload? Or do you want a powerhouse workstation that you can add lots of functionality to? The form factor will also play a role into what expansion slots you might want to use. Understanding motherboards and their characteristics can be a big plus when fixing hardware issues, since things like the type of RAM module or processor socket are dependent on the kind of motherboard they need to fit into. Let's say you're responding to a ticket for a user who's having video problems. You don't want to make it all the way to their desk only to realize the graphics card you bought as a replacement doesn't fit the motherboard their computer uses. You will learn more about customer service and troubleshooting tactics later on in this course. But for now, make sure that your motherboard can fit any replacement or upgrade that you want to implement. So, before we get into computer storage, we need to fill in some gaps. I'm referring to things like gigabytes, bits, etc. But we actually haven't talked at all about what those metrics mean. Sorry, I got a gigabit ahead of myself. As you might have guessed, these terms refer to data sizes. The smallest unit of a data storage is a bit. A bit can store one binary digit, so it can store a 1 or 0. The next largest unit of storage is called a byte, which is comprised of 8 bits. A single byte can hold a letter, number, or symbol. The next largest unit is referred to as a kibibyte, but we typically use the term kilobyte. A kilobyte is made up of 1024 bytes. If you're curious why 1 kilobyte refers to 1024 bytes and not 1000 bytes, you can read more about that in the next supplemental reading. For now, here's a quick data conversion chart. How much does 500 gigabytes even mean? Let's take a look at the size of an average music file, which is about 3 megabytes. On a 500 gigabyte machine, that's approximately 165,000 music files. That's a lot of music. We store all of our computer's data on our hard drive, which allows us to store our programs, music, pictures, etc. Have you ever had an issue with your computer and lost all the data that was on your hard drive? Yeah, me too. It was the worst. This actually happens a lot, and you'll probably encounter it as an IT support specialist. Make sure you back up your data to be safe. This means you should copy or save your data somewhere else, just in case something goes wrong and your hard drive crashes. That way, you won't lose all your data. There are two basic hard drive types used today. Hard disk drives, or HDDs, use a spinning platter and a mechanical arm to read and write information. The speed that the platter rotates allows you to read and write data faster. This is commonly referred to as RPM, or revolution per minute. A hard drive with a higher RPM is faster, so if you go out and buy a hard drive today, you might see something like a 500 gigabyte with 5400 RPM. HDDs are prone to a lot more damage because there are a lot of moving parts. This susceptibility to damage went away with a new type of storage called solid-state drive, or SSD. SSDs have no moving parts. Are you familiar with a USB stick? SSDs operate in a similar way. The information is stored on microchips, and data travels a lot faster than HDDs. The form factor for SSDs is also slimmer compared to their HDD cousins. Sounds great, doesn't it? So why doesn't everyone use SSDs? Well, both have their pros and cons. HDDs are more affordable, but they're more prone to damage. SSDs are less risky when it comes to losing data, but they're also more expensive. So you may not buy as much memory storage in SSDs than what you can get in HDDs. Believe it or not, there are even hybrid SSD and HDD drives out there. They offer SSD performance where you need it for things like system performance, such as booting your computer, along with hard disk drives, but less important stuff like basic file storage. There are a few interfaces that hard drives use to connect to our system. ATA interfaces are the most common ones. The most popular ATA drive is the serial ATA, or SATA, which uses one cable for data transfers. SATA drives are hot swappable. Great term, don't you think? It means you don't have to turn off your machine to plug in a SATA drive. SATA drives move data faster and use a more efficient cable like this one than its predecessors. SATA has been the de facto interface for HDDs today, but people quickly found that using the SATA cable wasn't good enough for some of the blazing fast SSDs that were coming on the market. The interface couldn't keep up with the speeds of the newest SSDs, so another interface standard was created called NVMe Express, or NVMe. Instead of using a cable to connect your drive to your machine, the drive was added as an expansion slot, which allows for greater throughput of data and increased efficiency. In order to get our computer to work, let's give it some power. Computers have a power supply that converts electricity from your wall to something usable. There are two types of electricity: DC, or direct current, which flows in one direction, and AC, or alternating current, which changes directions constantly. Our computers use DC voltage, so we have to have a way to convert the AC voltage from our power company to something we can use. That's what our power supply does. It converts the AC we get from the wall into low voltage DC power that we can use and transmit throughout our computer. So let's talk about power supplies. I actually have one right here. Let me show you how one looks like. Take it out right here. So most power supply units have a fan, which is right in here. They also have voltage information, which is normally listed underneath or on the side, and cables like this one to power your motherboard, and a power cable. Have you ever plugged one of your devices into the wall outlet and fried your device? If you haven't, you're really lucky. After completing this lesson, hopefully you'll know how to avoid that situation. To understand electricity, let's use the example of water pipes. Our sinks have a faucet that's connected to a pressurized water tank. When we turn on the faucet, water comes out. This is sort of like how electricity works. When we plug an appliance into a wall outlet and turn it on, a flow of electricity comes out. If we added more pressure to our water tank, would more water come out of it? The higher the pressure, the more water there will be. When it comes to electricity, we refer to the pressure as voltage. So when I was on vacation, to my surprise, when I plugged in the 120 volt appliance into a 220 volt outlet, the power came bursting through and fried my charger. If it was the other way around and a 220 volt appliance was plugged into a 120 volt outlet, I wouldn't have seen the same outcome. I'll still be able to get electricity, but slowly. This would be similar to if a water tank was only half pressurized. It would draw water, but slowly. In some cases though, this can deteriorate the performance of the device and cause damage in the long term. As a general rule, be sure to use the proper voltage for your electronics. We refer to the amount of electricity coming out as current or amperage, and it's measured in amps. We can think of amps as pulling electricity as opposed to voltage, which pushes electricity. Amps will pull as much electricity needed, but voltage will just give you everything. Look on the back of one of your device chargers. You might see something like 1 or 2.1A. Charging a device with 2.1 amps will actually charge your device faster because it's able to pull more current from a 2.1 amp than a 1 amp charger. Finally, the other important part of the electricity that you will need to know is the wattage. Wattage is the amount of volts and amps that a device needs. If your power supply has too low of a wattage, you won't be able to power your computer, so make sure you have enough. This doesn't mean that if you have a large power supply, you'll overpower your computer. Power supplies just give you the amount that your system needs. It's best to err on the side of large power supplies. You can power most basic desktops with a 500 watt power supply, but if you're doing something more demanding on your computer, like playing a high resolution video game or doing a lot of video production and rendering, you'll likely need a bigger power supply for your computer. On the other hand, if all you're doing is just browsing the web, the power supply that comes with your computer should be fine. All kinds of issues are caused by a bad power supply. Sometimes the computer doesn't even turn on at all. Since power supplies can fail for lots of reasons like burnouts, power surges, or even lightning strikes, knowing how to diagnose power issues and replace a failed power supply is a skill every IT support specialist should have in their toolbox. So let's take a look at the back of our computer again. Here you'll see lots of connectors or ports we can plug in different objects like a mouse, keyboard, and a monitor. These are known as peripherals. A peripheral is basically anything that you connect your computer externally that adds functionality. You probably used USB devices before. USB, also known as Universal Serial Bus devices, are the most popular connections for our gadgets. USB has gone through lots of changes since inception. You'll most commonly encounter USB 2.0, USB 3.0, and 3.1 in today's system. Here's a quick rundown of the different versions. USB 2.0 transfer speeds of 480 megabytes per second. USB 3.0 transfer speeds of 5 gigabytes per second. USB 3.1 transfer speeds of 10 gigabytes per second. In the chart, let's pay attention to the details. Using capital M, lowercase b, /s, instead of using capital M, capital B to reference transfer speed. These are actually different units. MB is megabyte, or unit of data storage, while capital M, lowercase b, /s is a megabit per second, which is a unit of data transfer rate. People often mistake speeds of 40 megabit a second to mean that you can transfer 40 megabytes of data per second. Remember that 1 byte is 8 bits, so to transfer a 1 megabyte file in a second, you will need an 8 megabits per second connection speed. So to transfer 40 megabytes of data in a second, you will need a transfer speed of 240 megabits per second. You'll also need compatible USB ports to go with your devices. If you connect a USB 2.0 device into a USB 3.0 port, you won't get 3.0 transfer speeds. But you can still use the port since it's backward compatible, meaning older hardware will work with newer hardware. The ports are easy to differentiate. Let me show you. In general, USB 2.0 are black and USB 3.0 are blue, and 3.1 ports are teal. This may change depending on manufacturers. There are lots of types of USB connectors, and you can read about all of them in the supplemental reading right after this video. Check it out. Back to USB connectors. The most recent one is a Type-C connector, which is meant to replace many peripheral connections. It's quickly becoming a universal standard for display and data transfer. In addition to USB peripherals, you should also be aware of display peripherals. There are some common input standards to know. Most computer monitors will have one or more of these connections, but you might encounter some older standards too. DVI. DVI cables generally just output video. If you need to hook up a monitor or projector for a slide presentation and you want audio too, you may be out of luck. Instead, you want to look at one of the following cables. HDMI. This has become a standard in lots of televisions and computers nowadays. It outputs both video and audio. Another standard that's become popular among manufacturers is a DisplayPort, which also outputs audio and video. In addition to audio and video, USB Type-C can also do data transfer and power. As an IT support specialist, you'll work with peripherals like USB devices and display devices a lot. Now, you'll be able to distinguish between the major types. In the next lesson, we're going to learn how our computer initializes all of the hardware we've talked about. Isn't the history of computers super interesting? I love going back in time and seeing how we got to this exciting point in computing. You've already taken the first few steps to building your foundational knowledge of IT. And before we dive deeper, I'd like to take a moment to introduce myself. My name is Devin Sridharan. I've been working in IT for 10 years. I'm a corporate operations engineer at Google, where I get to tackle challenging and complex IT issues. Thinking back, my first experience with tech began when I was about 9 years old, when my dad brought home the family's first computer. I remember my dad holding a floppy disk and telling me that there was a game on it. To my dad's amazement, I somehow managed to copy the game from the disk onto the computer's hard drive. While it might seem like a trivial task now, this device was just so new to us back then. Sure, I loved the different games I could play, but what I really loved was tinkering with the machine, trying to get it to do what I want it to do. While that floppy disk and computer might have ignited my passion for technology, it was actually my first few job experiences that really started to shape my IT career. One was in retail, selling baby furniture, and the other was at a postal store where I helped customers ship their packages and became the one-person IT crew. It might sound odd that working in retail inspired my career, but I realized I really enjoyed communicating with customers, trying to understand their needs and offering a solution. My first experience working directly in IT was in college as an IT support specialist intern. From there, I worked as an IT consultant to decommission an entire IT environment. This was my first experience working directly with large IT infrastructure and pushing myself outside my comfort level as a college student. I bring up these few jobs for a reason. These experiences helped shape my career in IT. I knew at that time that I wanted to go into tech, but I struggled where I wanted to focus my career. Starting at Google as an IT generalist allowed me to experience many different areas of technology. It allowed me to figure out the jobs I didn't want to do before I was able to identify exactly what I did want to do. I'm really passionate about IT infrastructure, but you can't understand infrastructure until you understand hardware. So let's dig in. In IT, hardware is an essential topic to understand. You might find yourself replacing faulty components or even upgrading an entire fleet of machines one day. By the end of this lesson, you'll be able to describe all the physical parts of a computer and how they work together. You'll even be able to build your own computer. Once you figure out how one computer works, you'll be able to understand how any type of computer works. Excited? I am. Let's get started.
We introduced the concept of an operating system in earlier lessons. But what is it exactly? A lot of us hear the term operating system and think of the interfaces of our desktops and phones, like the menus, buttons, and backgrounds. Technically, these are part of the operating system, but it's a little more complex than that. An operating system is the whole package that manages our computer's resources and lets us interact with it. There are two main parts to an operating system, the kernel and the user space. The kernel is the main core of an operating system. It talks directly to our hardware and manages our system's resources. As users, we don't interact with the kernel directly. Instead, we interact with the second part of an operating system, the user space. The user space is basically made up of everything outside the kernel. These are things that we interact with directly, like system programs, user interfaces, etc. When we say operating system, we're talking about both the kernel and the user space. There are hundreds of operating systems out there, but we'll focus on the major ones used in IT. Windows, Mac, and Linux. The Windows OS is developed by Microsoft and used widely in the business and consumer space. Most PCs you buy come with Windows as the default operating system. PC means personal computer, which technically means a computer that one person uses. But in today's world, PC is more commonly referred to as a Windows computer. So we'll just refer to a PC as a Windows computer from here. macOS by Apple is mainly used in the consumer space. If you buy an Apple computer, it'll come with macOS preloaded. The last operating system we'll dive into is the Linux operating system. Linux is an open source operating system, which means its software is free to share, modify, and distribute. Linux is used heavily in business infrastructure and in the consumer space. Linux itself is actually a kernel developed by Linus Torvalds. Because of the way it evolved, we call the Linux kernel the Linux operating system. Today, Linux has become a huge community effort with developers all over the world contributing to its success. Because Linux is open source, lots of different organizations package their own version of it. Operating systems like Windows or Macintosh, on the other hand, are solely developed by their respective companies. We call these different Linux OSs distributions. Some common Linux distributions are Ubuntu, Debian, and Red Hat. Another operating system that has started to gain popularity is Chrome OS, but we won't go into detail on that one. You can read more about it in the supplemental reading right after this video. We also won't go over any of the operating systems used in mobile devices like Android OS, iOS, and Windows 10 Mobile. But you should be aware that mobile phone operating systems are quickly overtaking their desktop counterparts in terms of quantity. Mobile phone usage around the world is more prevalent than desktop computers. You can read more about this in the supplemental reading. But in this course, we're only going to focus on the Windows and Linux operating systems, since you'll most likely work with them in IT support. One cool thing to call out is that Chrome OS and Android OS both run the Linux kernel underneath the hood, so there's a chance you've already worked with Linux and didn't even know it. There are lots of operating systems out there, and they all share common characteristics. If you're able to understand the basic building blocks of one OS, you can apply that to any operating system and understand how it works. In IT support, it's super common to work with many different operating systems, from desktop OSs to smartphone OSs and more. Throughout the rest of this module, we're going to learn what an operating system is. More specifically, we're going to learn about the two components that make up an operating system, the kernel space and the user space. Before we get there, let's do a rundown of the basics. The kernel does file storage and file management. You can compare it to a physical office file where we store data in paper form. A computer file is just data that we store. And a file can be anything, a Word document, a picture, a song, literally anything. A file system is how we manage these files. Just like in an office, we use a system to store our files. We don't just put all our files in one cabinet. That would be seriously messy. Instead, we organize those files in folders or directories to make them easier to find. There are lots of different types of file systems, which we'll cover more in depth in future videos. Another important function of the kernel is process management. We have many programs that we want to run on our system. To run them, we manage the order they run in, how many resources they take up, how long they run, etc. Our kernel helps us do this with its process management capabilities. For example, you've probably used your computer to do several tasks at once. Maybe you write in a text document while listening to music or playing a video. The process scheduler is part of the kernel that makes this multitasking possible. It switches the execution of each different process on the CPU faster than you can blink, and it gives you the illusion that things are happening simultaneously. Next up is memory management. Our kernel optimizes memory usage and makes sure our applications have enough memory to run. We won't get into too much detail right now, so stay tuned for more on this in the next few videos. The last important function that a kernel performs is input-output, or I/O management. This is how our kernel talks to external devices like disks, keyboards, networks, connections, audio devices, and more. I/O management is anything that can give us input or that we can use for output of data. If you've ever saved a file to disk, clicked a mouse button, or used a microphone when video chatting with a friend, you've got the kernel's ability to manage I/O to thank. And that's a basic rundown of the main functions of the kernel: file management, process management, memory management, and I/O management. Finally, we'll talk about the other component of an operating system, the user space. The user space is everything outside the kernel. These are the things that we interact with directly, like programs such as text editors, music players, system settings, user interfaces, etc. By the end of this module, you'll hopefully have a solid understanding of all these functions of an operating system. Let's start by taking a deeper dive into the kernel's file management. Imagine if you had to store a single file in a cabinet. That's not so bad, right? What if instead of one file, you had to store 100,000? Can you see a problem here? Well, on our computers, we can easily store hundreds of thousands of files, if not more. Problem solved? Not quite. We have to be able to keep track of all these files. The kernel handles file storage and file systems on our machines. And in this lesson, we're going to dig a little deeper on how it does that. There are three main components to handling files on an OS: the file data, metadata, and file system. Let's start with the file system. When we have a brand new hard disk that we want to store data on, we need to erase and configure the disk. This way, our operating system can read and write data to it. This is important since it's how our operating system keeps tracks of files. So it must know what kind of file system is used. There are lots of file systems, and they're used for different purposes. Some file systems support the storage of large amounts of data, others only support small amounts. They can operate at different speeds and have varying resiliency towards file corruption and so on. We won't get into which file system is best. That's for you to decide. But the major OS manufacturers have their own unique file systems that they recommend. For Windows, the major file system that's used is NTFS. It was introduced in the previous version of Windows OS, Windows NT, and it includes many features like encryption, faster access speeds, security, and more. Microsoft is developing another file system called ReFS, but it isn't quite ready for consumer use just yet. If you're interested in learning more, you can read more about it in the next supplemental reading. For macOS, the default file system is HFS+. It's journaled, which means it does a better job at saving your disk state in case of a failure. This is a feature on other types of file systems like NTFS. For Linux, different distributions will use different file system types. A standard for file systems for Linux is ext4, which is compatible with older ext file systems. In general, different file system types don't play nicely with each other. You might not be able to easily move files across different file systems depending on the file system type. A good guideline to use is just to use the file system that your operating system recommends. You can read more about the different types of file systems in the supplemental reading. Another important part of file management is the storage of actual file data. We write data to our hard drive in the form of data blocks. When we save something to our hard disks, it doesn't always sit in one piece. It can be broken down into many pieces and written to different parts of the disk. Block storage improves faster handling of data because the data isn't stored on one long piece, and it can be accessed quicker. It's also better for utilizing storage space. Lastly, we need to keep the metadata that contains the information about our file. There's a lot of information about our file that we want to know, like who created it, when it was last modified, who has access to it, and so on. The file metadata tells us everything we need to know about our file. It also tells us what type of file it is. A file extension is the appended part of a file name that tells us what type of file it is in certain operating systems. Take cool_image.jpg. JPEG is a file extension associated with image files. You'll see different types of file extensions like this when you're working with your operating system. A working knowledge of file systems and the differences between them is a great skill to have in your IT support specialist toolbox. It can be super useful when you need to do things like recover data from damaged disks or explore ways to boot from two different kinds of operating systems, like Windows and Linux, on the same computer. One of the most important tasks that our kernel performs is process management. A process is a program that's executing, like our internet browser or text editor. A program is an application that we can run, like Chrome. Take note of the difference. We can have many processes of the same program running at the same time. Think of how many Chrome windows you can open. These are all different processes for the same program. When we want to run our programs, we have to dedicate computer resources to them, like RAM and CPU. We only have a finite amount of resources, and we want to be able to run multiple programs. Our kernel has to manage our resources efficiently so that all the programs we want to use can be run. Our kernel doesn't just dedicate all of our computer's resources to one process. Our system is actually constantly running multiple processes that are necessary for it to function. So our kernel has to worry about all of these processes at once. When a program wants to run, a process needs to be created for it. This process needs to have hardware resources like RAM and CPU. The kernel has to schedule time for the CPU to execute the instructions in the process. But there's only one CPU and many processes. How is the CPU able to execute multiple processes at once? It actually doesn't. It executes processes one by one through something known as a time slice. A time slice is a very short interval of time that gets allocated to a process for CPU execution. It's so short that you don't even notice it. I mean, it's super short. The CPU executes one process in milliseconds, then executes another process, then another. To the human eye, everything looks like it runs simultaneously. That's how fast the CPU works. If your computer is running slowly and your CPU resources are being maxed out, there could be many factors at play. It's possible that one process is taking up more time slices than it should. This means that the next process can't be executed. Another possibility is that there are too many processes that want CPU time, and the CPU can't keep up with them. Whatever the case may be, even though the kernel does its best to manage processes for us, we might need to step in manually from time to time. We'll talk about how to manage processes in a later course. The kernel creates processes, efficiently schedules them, and manages how processes are terminated. This is important since we need a way to collect all of the previously used resources that active processes were taking up and reallocate them to another process. Remember that when a process runs, it needs CPU time, but it also needs memory. When processes are run, they have to take up space in memory so that the computer can read and load them quickly. However, compared to our hard disk drives, memory comes in smaller quantities. So to give us more memory than we physically have, we use something called virtual memory. Virtual memory is the combination of hard drive space and RAM that acts like memory that our processes can use. When we execute a process, we take the data of the program in chunks we call pages. We store these pages in virtual memory. If we want to read and execute these pages, they have to be sent to physical memory or RAM. Why don't we just store the entire program in RAM so we can execute it quickly? Well, you could, if it was small enough, but for large applications, it would be wasteful. Have you ever worked in a word processor and then gone to a menu you don't normally use and noticed the application slow down a little? It's because your computer had to load the page for that menu from virtual memory into RAM. We don't use all the features of our application at once, so why load it up at once? It's similar to cooking a recipe from a cookbook. You don't need to read the whole book just to make one recipe. You only need to read the pages of the recipe you're currently using. When we store our virtual memory on our hard drive, we call the allocated space swap space. When we get into practical applications of disk partitioning, we'll allocate space for swap. The kernel takes care of all of this for us, of course. It handles the process of taking pages of data and swapping them between RAM and virtual memory. But the kernel isn't the only hard worker around. You've done great getting through the lessons so far. Nice work. Up next, we'll tackle I/O management. See you there! So far, we've learned how hard our kernel works by handling files, managing file storage, juggling all the different processes running on our computer, and allocating memory. Another important task that our kernel handles is managing input and output. We refer to devices that perform input and output as I/O devices. These include our monitors, keyboards, mice, hard disk drives, speakers, Bluetooth headsets, webcams, and network adapters. These I/O devices are all managed by our kernel. The kernel needs to be able to load up drivers that are used so that we can recognize and speak to these different types of hardware. When the kernel is able to start up the drivers to communicate with hardware, it also manages the transfer of data in and out of the devices. I/O doesn't just mean the transfer of data between us and our devices. The devices also need to be able to talk to each other. Our kernel handles all the intercommunication between devices. It also figures out what the most efficient method of transfer is, and it tries its best to make sure our data doesn't have errors during process. When you're troubleshooting or solving a problem with a slow machine, it's usually some sort of hardware resource deficiency. If you don't have enough RAM, you can't load up as many processes. If you don't have enough CPU, you can't execute programs fast enough. If you have too much input coming into the device or too much output going somewhere, you'll also block other data from being sent or received. It's slow is one of the most common problems you'll solve in an IT support role. Knowing the potential sources of that slowness is a big help when you're trying to narrow down the cause of the latency. Troubleshooting is such an important part of any IT support role. That's why we'll share some troubleshooting best practices in detail in upcoming lessons of this course. Beyond desktop support, identifying the source of a resource bottleneck in a server or large IT system like a web application can unlock performance gains and new heights of responsiveness for your users. Okay, we've covered the kernel's major responsibilities. Now, let's discuss the final major aspect of an operating system: how humans interact with it. This is what we call the user space. When we interact with an operating system, we want to do certain functions like create files and folders, open applications, delete items. You get the idea. There are two ways that we can interact with our OS: with a shell or a graphical user interface. There are also some shells that use graphical user interfaces, but will work with a command line interface or CLI shell for the most part. This just means that we'll use text commands. A graphical user interface, or GUI, is a visual way to interact with a computer. We use our mouse to click and drag, to open folders, etc. We can see everything we do with it. You probably use a GUI every day without realizing you're using one. To watch this video, you probably used a GUI, clicking icons and navigating menus to open your web browser and navigate to the Coursera website. People usually recognize a device or product based on its GUI. You might be able to spot the difference between a computer running Microsoft Windows or Mac OS based on the design of the windows, menus, and icons. You've probably seen GUIs in other places too, like mobile phones and tablets, ATM machines, and airport kiosks. A shell is basically a program that interprets text commands and sends them to the OS to execute. Before we had fancy visual interfaces, commands like create a file had to be typed out. While we have GUIs today, the shell is still commonly used to run commands, especially by power users. Power users are above average computer users. In Linux especially, it's essential that you actually know commands, not just a GUI. This is because most of the Linux machines you interact with in IT support will be accessed remotely. Most of the time, you won't be given a GUI. There are lots of different types of shells. Some have different features, some handle performance differently. It's the same concept behind different operating systems. For our purposes, we'll just be using the most common shell, Bash or Bourne Again shell in Linux. There's also a shell for Windows called PowerShell, but we won't be covering it here. You'll learn more about Windows PowerShell in the third course of this program, Operating Systems and You, Becoming a Power User. Throughout this program, we'll learn how to use the Windows GUI and Windows Shell PowerShell. You might be thinking, but it's easier for me to navigate a GUI than it is to use commands to do the same thing. So why would I want to learn both? I can't stress this enough. It's vital for you to know how to use a shell in an IT support role. Some tasks can only be completed through commands. In more advanced IT roles, you might have to manage thousands of machines. You don't want to have to click a button or drag a window on every machine when you can just run a command once. You're actually going to learn how to automate this in a later course. Using a GUI and shell isn't all you'll be doing. We'll also interact with our operating system through applications. There are system applications and libraries that we use on a day-to-day basis, like the login application, system settings, and more. Throughout this course, you'll learn more about how to use system applications. And we'll even get hands-on with the applications used in your operating system. Imagine this scenario. You're playing your favorite video game and you finally get to the big boss. You spent countless hours finding this boss, neglecting all other responsibilities like your job, school, even hygiene. That's pretty gross, but I get it. So you're right about to kill the big boss when suddenly your game console shuts off completely. You'd probably freak out for a second, but then you remember, it's okay. You saved the game before the boss came along, so now you can turn it back on and you'll be at the same spot. But then your console shuts off again. This happens over and over. You, like most people, are devastated. You fly into a fit of rage, but then, just before you toss your console out, you make one last-ditch effort and yell, "Tell me what's wrong with you!" Suddenly, you hear a faint voice telling you what you want to hear. Wouldn't that be amazing? Sure, that scenario was a bit exaggerated. But my point is that our computers actually can talk to us and tell us what's wrong. Maybe they won't whisper answers to us, but they speak to us in the form of logs. Logs are files that record system events on our computer, just like a system's diary. Our computer will record events like when it was turned on, when a driver was loaded, and even when something isn't working in the form of error messages. In all operating systems, logs are kept so we can refer back to them when we need to find out something that happened. But logs can be hard to navigate because our computer will essentially record everything. Here's what a log looks like. As you can see, it can be tough to make your way through a log. But with a little bit of elbow grease, we can figure out what happened on our computer and piece together a solution. We'll see an example of how a log is useful in figuring out an issue in a later lesson. We'll dive into the technical details of logs in a later course. For now, just be aware that we can investigate details about our computer that aren't obvious to us. Unfortunately, our computers, cars, and machines don't have a little voice that tells us what's wrong when there's a problem. But by the end of this program, you'll be able to navigate and read logs, so you won't even need it. In this lesson, we're going to learn how our operating system starts up. As an IT support specialist, you'll probably work on lots of computers that won't start. It's important to know the steps an operating system takes so you can help diagnose this sort of issue. Booting a computer or starting a computer comes from the phrase to pull oneself up by one's bootstraps. Basically, it means to start from nothing and follow a series of steps to arrive at a fully operational system. When we start up a computer, we'll use the term boot. For most operating systems, the boot process follows a general pattern, much like how we have different cars start up in the same way. Put in the key, turn on the ignition, etc. Here's a rundown of the boot process. First, the computer is powered on. Remember when we learned about the BIOS UEFI in earlier videos? The BIOS UEFI is a low-level software that initializes our computer's hardware to make sure everything is good to go. So next, the BIOS UEFI runs a process called the Power On Self-Test, or POST. The POST performs a series of diagnostic tests to make sure that the computer is in proper working order. Next, depending on the BIOS UEFI configuration, a boot device will be selected. Devices that are attached to our system, like hard drives, USB drives, CD drives, etc., are configured in a certain boot order. The devices will be checked in this order, and the computer will search for what's known as a bootloader. The bootloader is a small program that loads the operating system. Once our computer finds a bootloader on a device in the listed order, it'll start to execute this program. This will then start to load a larger and more complex program, and eventually loads our operating system. Once the bootloader loads up our operating system, our kernel gets loaded. The kernel controls access to our computer's resources. It also loads up drivers and more so that our hardware can talk to our software. Next, essential system processes and user space items are launched. These include processes like user login, spinning up a desktop environment, and more, which basically allows us to interact with our system. And that's it. After these simple steps, you'll be able to get to work. In the last lesson, you learned how an operating system boots up. It's an important concept to understand since you'll be faced with troubleshooting boot-up issues in IT support. Now, we're going to walk through the steps to select and install an operating system. We're going to focus on operating systems in the IT space. First, we'll talk about deciding which operating system to install in a business setting. Second, we'll dive into the overall process of installing an operating system. So how do you decide which operating system to install? Well, you need to ask yourself a couple of questions. Has the decision already been made? The operating systems in use by an organization have a lot to do with the applications and systems that they need to run. Are you working with an organization or service that requires the use of a specific operating system? If so, you're done. That was easy. If a decision hasn't been made on what OS to use, or if you're looking for an operating system for personal use, then you need to ask yourself what software will need to be run on this device. In lots of cases, the software will be designed to run on a specific operating system. It's also possible that the software is cross-platform, meaning it can run on more than one operating system. Another question to ask is what hardware will be used. Modern operating systems do a pretty good job of supporting common hardware. You should keep in mind that some manufacturers allow their operating system to be only installed on their hardware. Still a little confused about which operating system is best for you or your organization? Check out the supplemental reading right after this video to learn more. There's one more thing I should call out. Remember that we have different CPU architectures, 32-bit and 64-bit. Our operating systems will also be optimized for this architecture, so make sure that the CPU and OS are compatible. If you have a 64-bit CPU, you should also install the 64-bit version of the operating system you choose. Okay, now that you've chosen an operating system that you want to use, let's work on getting it installed on our hardware. Many computers come with an operating system pre-installed. If you boot the computer in this condition, the operating system will continue from whatever point the vendor left it at. You'll need to do a couple of things to finish the installation, like choosing a computer name or host name, or configuring the network for the device. There's more, but we won't worry about that now. When we walk through an installation of an operating system, you'll be able to see this. If you're going to be installing an operating system from scratch, you can use different installation media. Some operating system manufacturers sell their operating system in disk form or USB form. Some let you do reinstalls directly over the internet. As an IT support specialist, you'll install an operating system many times, so using one single disk won't be time efficient or scalable. Scalability is an important concept that we'll cover later. If you want to scale or accommodate multiple computers, the added support is something you need to keep in mind. For now, you're only working with one computer, so let's focus on that. Let's just use a USB drive to install your operating system. Some OS manufacturers have their own special USB drives with the installation image, like Windows. For Linux, we can load up an OS onto any USB drive. You'll see what I mean by that in the next couple of videos. See you there! Before we start installing our operating system, we need to be familiar with the concept of virtual machines, or VMs. A virtual machine is just a copy of a real machine. Why would you want that? We've been working with physical machines so far, but there are cases in IT support where we need access to a machine that isn't physically in front of us. Let's say I have a Windows machine, and I want to learn another operating system like Linux. I don't want to buy another computer or have two separate operating systems on my disk. Instead, I can use an application like VirtualBox to install Linux and have it completely isolated from my machine. Virtual machines use physical resources like memory, CPU, and storage, but they offer the added benefit of running multiple operating systems at once. They're also easier to maintain and provision. Virtual machines have become a staple in many IT departments, since they allow IT support specialists to create new virtual computers on demand. They can also reclaim the resources they use when they're no longer needed. If you wanted to use software that's only available on one specific OS, it's easier to create a new virtual machine, use the software, and then delete the virtual machines once you're done. Throughout this program, you'll actually be using VMs to perform hands-on exercises. You'll be working on our Quick Labs platform, where you'll be presented tasks to complete from within a lab setting. We list out the specific tasks you'll need to complete, and once you complete the tasks, you'll get the credit for the lab. Let's go ahead and do a quick walkthrough. Okay, let's check out a sample lab. I'm going to navigate to one of the labs that you'll be working with later on. When you log into the lab, you'll be presented with a doc with instructions on what you need to do to complete the lab. If you see here at the top, you'll also have a time remaining countdown timer. This tells you how much time you have to complete the lab once you click the Start Lab button. In this very first Qwiklab that you'll do, we give you instructions on how Qwiklab works and how to log into your Qwiklabs instance. I won't go over how to do that for now, as you'll get to do that yourself in Qwiklabs. For now, I just want to show you how to connect to the Qwiklabs virtual machine. I'm going to go ahead and click Start Lab. This will create a temporary account for me on the Google Cloud Platform, or GCP, where our virtual machine will be hosted. Then I'll be given account information for the Google Cloud Platform. If I click Open Cloud Console, I'll be prompted to log in with this account information. I'm just going to copy and paste this information in the login window here. Once I'm in, I'll be prompted to agree to the terms of service. I've already read the terms of service, so I'm going to hit Accept. There might be another terms of service agreement you'll have to agree to when you're in the GCP instance. I'm going to go ahead and accept this agreement as well. Okay, now we're in the Google Cloud Platform. Don't worry about all this information in here. It's not important. What is important is on the left-hand side here. We're going to go to Compute Engine. Then we're going to go to VM Instances. Here, you'll see the Windows and Linux instances of this lab. That's right, you're going to be working with both operating systems in Qwiklabs. I'm going to connect to my Linux instance really quick by clicking the SSH button. Again, all of this information is explained in the Qwiklabs instructions. And bam! Now we're connected to a Linux virtual machine. Pretty neat, right? Once I'm in my virtual machine, I just do the tasks in the lab. Once I'm done with my lab, I just go back to Qwiklabs and click End. This will grade my work and automatically check that I completed what I needed to do in my lab, then remove my temporary GCP account access. Okay, now that we know what a virtual machine is, you can see how they can be extremely useful. We'll revisit VMs in the future and see their other many uses. We're covering a lot of ground fast. Since we're going to start installing operating systems soon, feel free to review these lessons to make sure you fully understand the fundamentals before moving on. The first operating system we're going to install is Windows 10 OS. This is the latest iteration of the Windows family operating system. If you buy the software in stores, it comes in a nifty USB drive. I have Windows loaded on a USB drive. I'm going to go ahead and insert the drive, then boot it in a minute. But first, let's make sure we have our BIOS UEFI boot order set to boot from the USB drive. Depending on what the manufacturer of your computer uses, you'll either hit F12 or some other key to access the BIOS settings. Looks good. Let's just let it run and we'll see it booting from the USB drive. Take note that your installation process might be slightly different depending on the version of Windows. Okay, I'm just going to click Next here. It's just asking for my language preference, my time and keyboard. Then I'm going to click the Install Now button. It's asking for a product key. I'm just going to go ahead and skip this. We'll do that later. And it's just asking me to agree to a software license term. So I'm just going to accept. Click Next. All right. Now it's asking which type of installation I want to do. I'm just going to click on Custom because I just want to install Windows. I select the drive I want to install it on. Okay, it looks like the computer restarted. Now it's just configuring updates. Once it's done updating, it's going to restart one more time. And now we're launched into the screen here that's asking us to enter in the product key. We're just going to go ahead and skip to this for now. We'll do this later. So I'm going to click Do This Later. And now it's asking if what kind of settings we want to use. We're just going to click Use Express Settings for now. Just want to start using our machine as quickly as possible. Okay, it's asking us to create an account for this PC. The first field is the username. A username is a unique identifier for a user account. I'm just going to go ahead and use my first name as my username. Next, I'll enter a password. Once that's done, we'll go ahead and finish our setup. It's starting to set up everything for us. Perfect. Now, here we are inside the Windows 10 operating system. Let's check it out. This is our user space. We have our desktop environment here where we can navigate our files, folders, and applications. The main screen here is called a desktop. In the bottom right corner here, we have a taskbar. This gives us quick options and shows us information like network connectivity, the date, system notifications, sound, etc. In the bottom left-hand corner here, we can access the applications, files, folders, and settings. You can also shut down, restart, and power off your computer from here. Let's move on to our system settings. In the main menu, go ahead and navigate to the settings. From here, you can change any of your system settings like display resolution, user accounts, network, devices, etc. Now, we're going to create a file in our operating system with our GUI. Let's create a file here on our desktop. All you need to do is right-click, and you'll see some options available. Then select New, then Text Document. Bam! Now we have a text file on our desktop. We just need to give it a name. How about My Super Cool File? And that's it! You just created a file in Windows. That wasn't so bad, was it? Now that we've seen how Windows is installed, let's go ahead and install the Linux operating system. Remember how I said that Linux has many different versions of their operating system called distributions? There are countless articles that highlights the pros and cons of the hundreds of distributions out there. We'll go with the most popular consumer distribution, Ubuntu. I've already loaded Ubuntu on a plain USB drive. Pro tip, since Ubuntu is open source, you can download the free operating system install image directly from their website and install it using whatever media you like. I've included a link to it in the next supplemental reading. I should also call out that you can't just copy the install file to a USB drive and expect it to work. It has to be copied in a way that makes the USB device bootable from our BIOS. To load the image onto your USB device and make it bootable, you can use a tool like Etcher.io. You can also check out the link to the tool in the reading right after this video. Okay, I'm gonna go power on. And remember, we're gonna make sure that we want to boot from the USB device. Alright, now that it's loaded, you'll see an option if you want to try using the operating system first, or just install the operating system. We're going to do a fresh install of the operating system. The Ubuntu logo will pop up, and then we're going to have to go through a couple of loading screens while the system is installing. Alright, we're just going to go ahead and skip through all of these and just pick the defaults for now. Alright, now it asks us for our name, a computer name or host name, then a username. The host name is used to identify the computer when it needs to talk to other computers. On our personal computer, it's common to just use our own names for our computer's name. But in IT organization, we want to choose a good host name that follows a certain standardization. We'll go over that in a later lesson, but for now, let's just use an industry standard for host name like username-location. So I'm going to go ahead and enter in my name, Cindy. Then for the host name field, I'm going to type Cindy-NYC. Then for the password, we're just going to enter a password here. Then we're going to confirm. All right, then we're going to hit next. And then it'll ask us to restart once it's done. Awesome, now that's restarted, let's go ahead and log in. Great, now we're in the Ubuntu desktop environment. Here you can see where applications are laid out. On the left-hand side here, we have a dock that we can add shortcuts to. This layout may change since Ubuntu is changing their desktop environment in the near future. To learn more about this, you can check out the next supplemental reading. On the top right-hand bar here, you'll see quick settings for your computer, like network connectivity, Bluetooth connectivity, sound, and volume. There's also the time, a menu to power off, restart, sleep, and log out of your machine. Let's click on this menu and select System Settings. From here, you can change your system settings like your screensaver, resolution, hardware settings, and more. Let's go back to our desktop and select this icon here for files. This opens up a window so we can view our files. You can see the different files and folders here. If I click on Computer, I'm taken to the main directory of my system. We're going to get to this in depth in a later course, so for now I'm just going to head back to my desktop. Now, let's do the exact same thing we did with our Windows machine and create a file. This time, let's just use commands in the shell. Because we're in a GUI, we don't have a program called bash that we run our commands in. Instead, we open up the search utility here and search for an application called Terminal. When you open up the terminal, you'll see your username, an @ symbol, the host name, colon, tilde, and then /desktop as your command prompt. This is used to show who's running the command. This will be more important in another course as you switch users. The last portion of the prompt shows you where you are in the computer. We'll learn more about this in a later lesson too, but you can see that we're currently in our desktop. You can verify that we're using the bash shell with a simple command, echo $shell. The echo command just prints out text options to the display. In this case, the argument $shell is the current shell, /bin/bash or bash. You could even do echo hello, and it would display hello, which isn't as useful. Okay, let's create a file in our shell. I'm going to use the touch command. Touch my super cool file. And here, you can see it made a file on our desktop. There are many different commands you can use to make a file, but the touch command is one of the simpler ones. Right now, it might be hard to understand why you have to memorize Linux shell commands when it's easier to use a Windows GUI. If you'll be working with any Linux machines, it's essential that you know these commands. Don't worry, by the end of this program, you should be super comfortable in the shell. Maybe you'll even run commands faster than you can in the GUI. The last operating system we'll go over is Apple's macOS. We won't go into too many details about how to use this OS. Instead, we'll focus on the ins and outs of the Windows and Linux OSs. But if you know one operating system, you'll be able to navigate any operating system. Fortunately, all Apple computers come with macOS pre-installed, so we'll just go through the important parts of the operating system. Okay, here's the desktop environment for our Mac. At the bottom here, you'll see a dock with shortcuts to your applications. In the top right, you've got the system information like the time and date, network connectivity, battery life if you have a laptop, and some other quick settings. In the top left here, you can see the Apple icon. This bar will change menu options depending on what application is open, but if you click on the Apple icon, you'll see more options. You can tell your computer to sleep, restart, and power off from here. The most important thing we want to look at is at the System Preferences menu item. This launches our system settings. From here, we can change any of our computer settings, like setting the orientation of our mouse scroll, adding and removing users, setting up printers, changing our screensavers, adding Bluetooth devices, and more. I'm going to click on the desktop now. You'll notice our top left setting changed from our System Preferences to Finder. Finder is the file manager for all Macs. If you open a new Finder window, you can navigate the files and folders on your Mac. If you right-click on a file, or if you're using a Mac laptop, you can use a two-finger click on a file to view more information and perform lots of different tasks. The Mac, which is a completely different operating system than Windows or Linux, operates in a very similar way with similar menu options. Wow, you've really come a long way. You've been introduced to the major operating systems used today, gotten to play around with the system, and even perform some common tasks. Nice work! It's important in any IT role to know the ins and outs of operating systems because you'll be interacting with them every single day. We have a separate course that teaches you all the essentials you need to navigate the Windows and Linux OSs. But for now, pat yourself on the back. You just took the first step towards understanding OSs. Installing, managing, and navigating operating systems are all tasks that you'll have to do daily as an IT support specialist. You may even find yourself doing this for hundreds, if not thousands of machines in your fleet one day. Before we send you to the next module, we have 2 assessments for you, which will test you on creating files with both Windows and Linux. You can always go back and review the videos again if you need a refresher. Otherwise, I will sign off for now, and we'll meet again in Course 3, Operating Systems and You Becoming a Power User. In the next module, you'll meet my friend and colleague Victor Escobedo, who's going to dig into the internet and networking.
When most people think of the internet, they think of a magical cloud that lets you access your favorite websites, shop online, and view a seemingly endless stream of cat pictures. But there isn't any magic involved. There's no mysterious entity that grants us a cat picture on demand. The internet is just an interconnection of computers around the world, like a giant spider web that brings all of us together. We call the interconnection of computers a network. Computers in a network can talk to each other and send data to one another. You can create a simple network with just 2 computers. In fact, you might already have your own network at home, connecting all of your home devices. Let's think on a bigger scale. What about the computers at your school or workplace? Are they in a network? They sure are. All of the computers there are linked together in a network. Can we link your home, school, and workplace networks together? We absolutely can. Your workplace connects to a bigger network, and that network connects to an even bigger network, and on and on. Eventually, you've got billions of computers that are interconnected, making up what we call the internet. You, like most people, probably access the internet through a browser like Mozilla Firefox, Google Chrome, Microsoft Edge, or something else. This is done through the World Wide Web. But don't make the mistake of thinking the internet is the World Wide Web. The internet is the physical connection of computers and wires around the world. The web is the information on the internet. We use it to access the internet through a link like www.google.com. The World Wide Web isn't the only way we can access the internet. Your email, chat, and file sharing programs are also ways you can access the internet. In the IT field, managing, building, and designing networks is known as networking. Networking is a super important and large field in IT. There are specialized jobs, college degree programs, and tons of literature dedicated entirely to networking. If you work in the IT field, it's super critical that you understand the fundamentals of networking. So, how does it all work? To answer that question, we're going to need a lot more time. Fortunately, we have a separate course entirely dedicated to this topic. We'll only cover the high-level overview of networking here. The internet is composed of a massive network of satellites, cellular networks, and physical cables buried underneath the ground. We don't actually connect to the internet directly. Instead, computers called servers connect directly to the internet. Servers store the websites that we use, like Wikipedia, Google, Reddit, and BBC. These websites serve content. The machines that we use, like our mobile phones, laptops, video game consoles, and more, are called clients. Clients request the content, like pictures, websites, from the servers. Clients don't connect directly to the internet. Instead, they connect to a network run by an internet service provider, or ISP, like CenturyLink, Level 3, Comcast, Telefonica, and things like that. ISPs have already built networks and run all the necessary physical cabling that connects millions of computers together in one network. They also connect to other networks and other ISPs. These other networks connect to the networks of Google, Reddit, and universities, basically all the other networks in the world. Together, they form one giant network of computers called the internet. But how do the clients know how to get to servers? Well, how would you send a letter to someone? You'd put your address on the letter and send it to the address of the person you're sending the letter to. Computers have addresses, just like houses. Computers on a network have an identifier called an IP address. An IP address is composed of digits and numbers like 100.1.4.3. When we want to access a website like www.coursera.com, we're actually going to their IP address like 172.217.6.46. Devices that can connect to a network have another unique identifier called a MAC address. MAC addresses are generally permanent and hard-coded onto a device. A sample MAC address can be something like this. When you send or receive data through a network, you need to have both an IP and a MAC address. You might be wondering why we need to have two different numbers to identify something. That's a good question. Think again of the letter analogy we used before. An IP address is your house address, while the MAC address is the name of the recipient of the letter. You want to make sure your letter gets to the right location and to the right person. A more simplified example of the letter delivery would go like this. I'm in New York City, and I got a letter that I want to send to a friend, May. May's halfway across the world in Tokyo, so our letter will go through lots of places before it reaches her. I put her name and address on there, and I also put my name and address on there too. When I drop my letter off at the post office, the mail person looks at it. He thinks, I don't know how to get to Tokyo from here, but there's a truck that's headed to Texas. He puts my letter in that truck. At the post office in Texas, a mail person looks at the letter and says, I don't know how to get to Tokyo from here, but we have a truck going to San Francisco. She puts my letter in that truck. At the post office in San Francisco, yet another mail person looks at my letter. He says, oh, there's a plane headed to Tokyo, and puts the letter on that plane. When it finally reaches Tokyo, the postman there says, oh, I know where May lives, and delivers the letter to her. Obviously, there are many more nuances to mail delivery than what I described, but this process is similar to how information gets routed across the internet. One thing to call out is that data that's sent through a network is sent through packets. They're little bits of data, and you guessed it, ones and zeros. It doesn't matter if it's pictures, email, music, or text. When we move data through the network, we break them down into packets. When a packet gets to its destination, it will rearrange itself back in order. Think of a packet like a letter. Let's actually look at this process again, but this time we'll use IP addresses and MAC addresses. Natalie has a computer with IP address 113.8.81.2, and she wants to go to google.com and search for pictures of cats. Before she does that, her computer has to send a packet to ask google.com if it can access their website. Our packet knows google.com's IP address is 172.217.6.46, but it doesn't know how to get there just yet. The packet travels from one place to another at each destination where it asks, hey, do you know where google.com is? Eventually, it'll be routed to another destination that can get the packet closer and closer to google.com. Once it reaches a destination that can deliver the packet to a server at google.com, Google will send Natalie a packet saying she can access an unlimited number of cat pictures. There are many technical details that we left out in this explanation, but don't worry, you'll learn all about the nitty-gritty in the networking course of this program. For now, this is what you need to know about the not-so-magic of the internet. Now that we understand what networks are, let's talk about how they're connected. There are a lot of ways you can connect computers to a network. We'll only cover a few of the major ones in this course. First, there's an Ethernet cable, which lets you physically connect to the network through a cable. On the back of the desktop we worked in the previous lessons, there's a network port that you plug your Ethernet cable into. Another way to connect to a network is through Wi-Fi, which is wireless networking. Most modern computing systems have wireless capabilities, like mobile phones, smart televisions, and laptops. We connect to wireless networks through radios and antennas. The last method we'll go over uses fiber optic cables to connect to a network. This is the most expensive method since fiber optic cables allow greater speeds than all the other methods. Fiber optic gets its name because the cables contain glass fibers that move data through light instead of electricity. This means that we send ones and zeros through a beam of light instead of an electrical current through a copper wire. How cool is that? But our cables have to connect to something. We don't just have millions of cables going in and out of computers to connect them together. Instead, computers connect to a few different devices that help organize our network together. The first device that your computer connects to is a router. A router connects lots of different devices together and helps route network traffic. Let's say we have 4 computers, A, B, C, and D, connected together through a router in the same network. You want to send a file from computer A to computer B. Our packets go through the router, and the router utilizes network protocols to help determine where to send the packet. We'll cover network protocols in the next video. For now, just know that our router uses a set of rules to figure out where to send our data. So, now our packet gets routed from computer A to computer B. Sweet. What if we wanted to send a packet to a computer not in our network? What if we wanted to send a packet to our friend Alejandro's computer? Alejandro is on a different network altogether. Fortunately, our router knows how to handle that too. The packet will get routed outside our network to our ISP's network. Using networking protocols, it's able to figure out where Alejandro's computer is. During this process, our packet is traveling across many different routers, switches, and hubs. Switches and hubs are also devices that help our data travel. Think of switches like mail rooms in a building. Routers get our letters to the building, but once we're inside, we use the mail room to figure out where to send a letter. Hubs are like company memos. They don't know who to send the memo to, so they send it to everyone. Working with network devices is important to understand because it's likely that one day you'll have users reporting problems accessing the internet. You'll want to investigate your way up the network stack. A technology stack, in this case a network stack, is just a set of hardware or software that provides the infrastructure for a computer. So the network stack is all the components that makes up computer networking. You might need to investigate the network stack in your job. You'd start with making sure the end user computers are working properly. Then you'd turn your attention to other possible points of failure, like the cabling, switches, and routers that work together to access the internet. We'll dive a little deeper into the different networking devices in the networking course. For now, let's route ourselves to the next lesson, the language of the internet. We talked briefly about the networking protocols our devices use to help our packets get from one destination to another destination. But what are they? There are lots and lots of network protocols used, and they're all necessary to help us get our packets in the right place. Think of network protocols like a set of rules for how we transfer data in a network. Imagine if you sent a letter to your friend Sasha, who lives in California, but your post office sends it out to another Sasha who lives out in New York. That would hopefully never happen, since the post office has rules that they follow to make sure your letter is sent to the correct address. Our networking protocols do the same thing. There are rules that make sure our packets are routed efficiently, aren't corrupted, are secure, go to the right machine, and are named appropriately. You get the idea. We'll cover specific network protocols later on, but there are two protocols that you need to know: the Transmission Control Protocol and the Internet Protocol, or TCP/IP for short, which have become the predominant protocols of the internet. The Internet Protocol, or IP, is responsible for delivering our packets to the right computers. Remember those addresses that computers use to find something on a network? They're called IP addresses, or Internet Protocol addresses. The Internet Protocol helps us route information. The Transmission Control Protocol, or TCP, is a protocol that handles reliable delivery of information from one network to another. This protocol was an important part of the creation of the internet, since it let us share information with other computers. We'll spend a lot of time diving into these protocols in the next course, the bits and bytes of computer networking, so stay tuned. For now, you've got a high-level understanding of how the internet works with TCP/IP. Lots of different ways to use the internet. We all know that. But I want to cover one of the more prevalent ways that people access the internet, through the web. All websites can be accessed through the web. Websites are basically text documents that we format with HTML, or Hypertext Markup Language. It's a coding language used by web browsers. Web pages are generally made up of very basic components. They contain multimedia content like text, images, audio, and video. When you want to navigate to a website, you would type in a URL like www.reddit.com. A URL, which stands for Uniform Resource Locator, is just a web address similar to a home address. Notice the www in the URL? It stands for World Wide Web. The second portion, reddit.com, is something we call a domain name. Anyone can register a domain name. It's just our website name. Once a name is taken, it'll be registered to ICANN, the Internet Corporation for Assigned Names and Numbers. Once a domain name is registered with ICANN, no one else can take that name unless it becomes available again. The last part of the URL, in this case, is .com, but you can also use different domain endings like reddit.net or reddit.org. The different domain name endings are standards for what type of website it might be. So a domain that ends in .edu is mainly used for educational institutions. Remember how computers use IP addresses to find another computer? Well, you can do the same if you wanted to find a computer on the internet. Let's go ahead and type 172.217.6.46 into a web browser and hit enter. Wait a minute, what happened? How come we're at Google's homepage? It turns out the IP address 172.217.6.46 maps to Google's homepage through a critical web protocol domain name system, or DNS. DNS acts like our internet's directory and lets us use human-readable words to map to an IP address. The computer doesn't know what google.com is. It only knows how to get to an IP address. With DNS, it's able to map Google's IP address with google.com. Every time you go on a website, your computer is performing a DNS lookup to find the IP address of the website name you typed in. This trick can be a good first step in diagnosing certain kinds of DNS issues. So if you're able to access a website by its IP address, but not its human-readable domain name, then there's a good bet that there's probably a problem somewhere in the DNS configuration your network is using. Understanding IP addresses can come in handy in all sorts of other situations you might encounter as an IT support specialist. The source of internet requests are usually identified by IP addresses in server logs. Many pieces of IT infrastructure need to have some kind of IP address configuration applied to them in order to work. DNS is a huge system, and we'll be discussing more about it later. Now that you understand the basics of how the internet works, I'll sign off for now and leave you in the very capable hands of my friend and colleague Gian Spicuzza. I'll see you again in Course 2, the bits and bytes of computer networking. But in the next lessons, Gian is going to talk about the incredible boom of the internet age.
You've learned what the internet is and a little bit about how it works. Now, we're going to take a step back and learn why it was created. But before we do that, I'd like to introduce myself. My name is Gian Spicuzza, and I'm a program manager in Android security. I help protect Android's 2 billion plus users by managing new security features for each of Android's desserts, or versions of Android. I've always loved technology, and I worked in IT since I was 16 and throughout university. I would fill my pastime reading about new tech and building servers from old computer parts in my basement. My earliest memory of working on tech is waiting for my parents to go to sleep so I could quietly dial up the internet while the phone was free and just browse websites all night long and read about random tech things. My first jobs were as a one-person IT crew at 3 nonprofit organizations. It was both stressful and really exciting to be responsible for everything, from configuring and administrating backup servers to just showing new employees how to access email and use their computers. I'm really excited to be here with you. I was never a really great test taker, and my grades reflected that. But I knew with hard work and perseverance, I could build a great career in IT. And so can you. So let's get started and dig in a bit more on the internet. The internet has become an essential part of our lives. Our bank accounts, entertainment, news, and education are all on the internet. It's important to learn why that is, since some of the original designs of the internet have reached their limitations. As an IT support specialist, you should understand what the future of the internet holds and why. Let's go back in time to the 1950s where it all started. Remember, back then computers were huge and bulky. If you were a programmer, you needed to directly interact with these massive computers. That would get real old real fast, especially if you had several people who wanted to use the only computing resource available. In the late 1960s, the US government spun up a project called DARPA. It went on to create the earliest version of the internet that we see today, with the ARPANET. Eventually, computer programmers were able to share a single computing resource by being able to remotely access the computer. But there was still a big problem. Networks couldn't talk to each other. It wasn't until the 1970s that we had a critical breakthrough in computer networking that fixed this problem. It was thanks to computer scientists Vinton Cerf and Bob Kahn who created the method we call the Transmission Control Protocol and the Internet Protocol, or TCP/IP. First, only a handful of computers in universities, governments, and businesses adopt TCP/IP. Then, hundreds. And then, in the span of 50 years, billions of computers. TCP/IP is the protocol that we use on the internet today. Finally, people around the world could send data to one another. But there was still a problem. The information they sent was just text. It wasn't centralized and it was pretty bland. Then, in the 1990s, a computer scientist by the name of Tim Berners-Lee invented the World Wide Web. It utilized different protocols for displaying information in web pages and became the predominant way of communication and accessing the internet. Anyone who had an internet connection at that time was able to access the information source of the World Wide Web. It's been 30 years since the creation of the World Wide Web. We've gone from sending simple email messages and viewing basic web pages to having video chats and instant news updates, order food, buy books, and even cars in a matter of seconds. Taking an online course like this wasn't even possible until recently. The creation of the internet that we know today was the culmination of knowledge and engineering from many brilliant scientists and organizations. If you want to learn more about the history of the internet, check out the supplemental reading and the networking course in this program. In the next video, we'll explore the limitations of the original designs of the internet and how these limitations affect us today. We've mentioned IP addresses a lot in this course, but we haven't actually gone into detail about them. There are actually different versions of IP addresses. The current protocol, Internet Protocol version 4, or IPv4, is an address that consists of 32 bits separated into 4 groups. Remember, 42 bits is 4 bytes, and 1 byte can be stored up to 256 values from 0 to 255. So IPv4 addresses can be something like 73.55.242.3. Even though it might seem like a lot of possible IPv4 addresses, there are less than 4.3 billion IPv4 addresses. There are way more than 4.3 billion websites out on the web today. Some IPv4 addresses are even reserved for special purposes, so the number of usable IP addresses is even less. A device that wants to connect to the internet needs to have an IP address. But devices around the world have already exceeded those numbers. So where have we been getting IP addresses? IP addresses have been able to keep up with the amount of devices in the world thanks to IPv6, or Internet Protocol version 6 addresses. IPv6 addresses consist of 128 bits, 4 times the amount that IPv4 uses, which means way more devices can have IP addresses. The adoption of IPv6 addresses has been slow but steady. Eventually, you'll start seeing more and more IPv6 addresses in the wild. An example IPv4 address can be something like 172.14.24.1, but an IPv6 address can be something like what you see here. Quite a bit of a difference, don't you think? Here's an analogy for how big this difference is between IPv4 and IPv6. With IPv6, there are 2 to the 128th power possible IP addresses. 2 to the 128th power is an insanely huge number. So huge that scientists had trouble describing with words just how big this number is. So here's an analogy. Think of a grain of sand. If you scoop up a handful, do you know how many grains you have in your hand? Probably a lot, but that's not even close to the number we're talking about. Now, take all the grains of sand in the entire world. Assuming there are roughly 7.5 times 10 to the 18th power grains of sand in the world, that still wouldn't be enough IPv6 addresses. Now, let's take all the sand from multiple Earths. Now you're close to what that number would be. It's a crazy large number. Just know that we won't be running out of IPv6 addresses anytime soon. Another mitigation tool that we've been able to use is NAT, or Network Address Translation. This lets organizations use one public IP address and many private IP addresses within the network. Think of NAT like a receptionist at a company. You know what number to dial to get to the company, and once you reach the receptionist, he can transfer your call to one of the private numbers inside the company. Now, instead of companies using hundreds of public IP addresses, they can just use one IP address. Remember the routers we talked about earlier? One task you might need to perform when you're an IT support specialist is to configure NAT on a router to facilitate communication between your company's network and the outside world. There are lots of other limitations that we've had to deal with. You'll learn more about them in the networking course. For now, you should have a general understanding of why IPv4 is so limiting for us today, and how IPv6 helps solve that problem. There's no doubt that the internet has made it much easier for us to connect with our friends and family, but it's also made it easier to connect with everyone else in the world. We're no longer confined to our local neighborhoods. Decades ago, if you wanted to sell something, you'd place your goods in your driveway and put up signs for a garage sale. The only way someone would see this is if they drove by your neighborhood and saw your sign. We got a little more savvy and started advertising in our local newspaper. We had to pay to list our ad, but at least we were able to reach more people in our neighborhood. Then the internet boom happened, and we could use sites like Craigslist to post an advertisement for free and reach more people in our city. Then we were able to sell to people outside of our city, to cities in other states. Eventually, we could sell to people outside of our own country, all thanks to the internet. Globalization is the movement that lets governments, businesses, and organizations communicate and integrate together on an international scale. It's been made possible by the internet and information technology. Countries can communicate with each other faster. News happening on the other side of the world reaches us before we can blink. And global and financial trade have increased dramatically. Globalization has transformed almost every aspect of human society as we know it. Media and social movements have become globalized too. In 2011, several countries in the Middle East started riots and protests against their government regimes, known as the Arab Spring protests. Because of outlets like social media, their movement gained worldwide attention, and citizens of many different countries banded together to take collective action. Social media movements like this have been going on for years, gathering together people from all over the world and unifying them under a single cause. The internet has also dramatically changed the way we consume entertainment. A few years ago, if you wanted to watch something on TV, you had to actually sit in front of your TV right when it aired, or else you'd miss it. Then we started recording our shows, first on VHS and then on things like TiVo, so we could watch them later. But now we have access to more TV shows and movies than we can ever watch in our entire lifetime right at our fingertips. What if you wanted to listen to a new song by your favorite band? You used to have to wait until they released their album in a store. And you couldn't just buy one song, you had to buy the entire album on a CD, cassette tape, or even a vinyl record back in the day. If you wanted to get the day's news, you had to wait until the next day when the newspaper would print it. Even then, you weren't able to get a fraction of a fraction of a fraction of the news you can get on the internet today. Retail stores aren't the only place you look when you want to buy something anymore. Now you can order food, clothes, books, and well, just about anything on the internet. But you don't just buy stuff off the web, you can even get an education. Colleges and universities worldwide are taking education out of the classroom and putting it into your homes. Online courses are becoming a popular way for people to get a quality education at a more convenient location, time, and price. And it's not just degrees. There's an almost infinite amount of educational tools available on the internet. A few years ago, all this information on the internet had to be reached through your laptop or desktop. Now, more than ever, people are going mobile and can access all of this information with their smartphones. It's truly an amazing time to be alive in this technological age. So the takeaway here is that the only constant in the field of technology is change. And as an IT support specialist, you'll have to stay on your toes to keep up with this dynamic, shifting landscape. You may have heard of the phrase Internet of Things, or IoT. This concept is pretty new, but already has a major impact on the future of computing. The concept is fairly simple. Basically, more and more devices are being connected to the internet in a smarter fashion. Did you know that there are now smart thermostats? Instead of manually programming them when you'll be out of the house, they'll just know when you leave and turn off the air conditioning for you. And it's not just your thermostat. Many companies out there are making smarter household devices. There are fridges that can keep track of what foods you have in there, toasters that can be controlled by your smartphone, lights that can change depending on your mood, and cars that drive you instead of you driving them. The world is moving towards connecting manual devices to the internet and making them smarter. These decisions have many societal implications though, especially when it comes to cybersecurity or personal privacy. But there's also a huge potential for IoT to completely transform the world in ways we have yet to see. In the future, people may be shocked to learn that we had to do manual things like make our own coffee or drive to the grocery store. While you may not experience working with an Internet of Things device, you should be aware that it will become a large part of the future of computing. You can learn more about IoT in the next supplementary reading. The added convenience made possible by the internet also makes it harder and harder for us to maintain anonymity. When you purchase something online, your buying habits can be logged and you may be targeted with marketing. Even when you want to do something simple, like book a dinner reservation, your name, phone number, email, and maybe even a credit card number are required. Now think about the information you post publicly. Name, pictures, family, friends, and even your location may be available to anyone online. Be aware of what you're sharing by reviewing the privacy policy of a service before you use it. It's up to you to decide if the trade-offs of a service are worth sharing your personal information. In most cases, companies are trying to build great products that make our lives easier. They may offer their products for free because you provide them with free data. Just make sure your information won't fall into the wrong hands. Privacy doesn't just affect us on a personal scale. It's also become a concern for governments. In Europe, data regulation and privacy are strictly protected to help EU citizens gain more control over their personal information. COPPA, or the Children's Online Privacy Protection Act, also regulates the information we show to children under the age of 13. There are many more examples of government regulation of privacy. It's no longer something we can think of on an individual scale. Another concern that's grown with the rise of the internet is the issue of copyright. Imagine you create a beautiful graphic and upload it on the web for your friends to see. Then some random stranger takes your graphic, claims it as their own, and sells it for profit. Thankfully, several companies have been founded and designed specifically to help solve this issue of copyright and intellectual property theft. There are also efforts in place that you've learned about, like open source projects that benefit from being on the internet. In these cases, open collaboration allows a project to thrive. On top of privacy and copyright considerations, computer security is another issue that you may face in both your personal and professional life. More and more companies are being targeted in cybersecurity attacks. For example, the WannaCry attack that started in Europe infected hundreds of thousands of computers across the world. The financial loss of that attack has been estimated at over $1 billion. Hospital computers were even infected. In a critical, life-threatening moment, every second matters. Not being able to perform basic medical duties, like pulling medical records, took time away from doctors and nurses, and more importantly, the lives of their patients. Before the WannaCry attack, there were lots of other worldwide attacks. In 2011, the Sony PlayStation Network was attacked, and around 77 million user accounts had personal information exposed. Everything from entire governments to businesses that handle the data of millions of people have been compromised. Computer security is no longer the job of specialized security engineers. It's everyone's responsibility. And as an IT support specialist, you'll need to have a fundamental understanding of computer security. You'll get to learn these fundamentals in the course IT Security, Defense Against the Digital Dark Arts, which I'll be teaching you. I spend every day working in security. I love working in the field because I get to help protect people and their devices from all over the globe. The security course in this program teaches you just that. You'll also learn what threats are out there and how you can prevent and mitigate them, and how to secure your workplace. Next up, you're going to meet my buddy, Phelan Vendeville, who's going to introduce you to software. But before that, we've got a quick quiz we've cooked up for you on all the topics we've covered so far. Take your time and good luck.
Video games, music players, and internet browsers are all different types of software that have completely different functions. Think of the apps on your phone and your laptop. We spend a lot of time interacting with this type of software, but we may not know how it actually works or gets added to our systems. In the last few videos, we learned about networking and the internet. There are tons of applications out there that require the internet to work. Think about it. Your social media apps, messaging apps, and others run off the internet. This internet integration isn't just magically added to your application. It's built in to require it to function. Before we go too far into the world of software, I want to call out some common terms related to software that you might hear. Coding, scripting, and programming are all terms that might seem a little blurry. They generally refer to the same thing, but they each have small distinctions. Coding is basically translating one language to another. This can be coding from English to Spanish, English to Morse code, or even English to a computer language. When someone builds an application, We refer to it as coding an application. Scripting is coding in a scripting language. We'll talk about scripting languages in a later lesson, but scripts are mainly used to perform a single or limited range task. There are languages we can use to build these. Programming is coding in a programming language. Programming languages are special languages that software developers use to write instructions for computers to execute. Larger applications like your web browser, text editors, and music players are all usually written in programming languages. When we use the term software, it generally refers to something that was programmed. We'll use these terms pretty interchangeably, so don't sweat the details. Now, onwards and upwards. So, what is software made of, and who builds it? It's a great question. Anyone who knows a programming or a scripting language can use it to write code. There's a huge demand for this skill set, and it's becoming easier for someone to learn to code. If you're going to be working in IT, it's important that you understand how software works and how it gets installed on your systems. You might encounter software errors or just good old-fashioned failures, and you need to understand how to deal with them. By the end of this module, you'll be able to understand what software is, how it works, and how to install it, remove it, and update it, all within the Linux and Windows operating systems. When you write content, create a piece of art, or engineer something, your work is protected for your use and distribution. There's usually some other caveats depending on the laws in your country. But in general, copyright is used when creating original work. Software that's written is also protected by copyright. Software developers can choose what they do with their software. For commercial software, it's common to let someone else use their software if they pay for a license. For non-commercial software, a popular option is making it open source. This means the developers will let other developers share, modify, and distribute their software for free. Score. Some amazing software efforts have been developed and advanced because of open source. One major example is the Linux kernel, which is used in the Android OS and in enterprise and personal computers. Hundreds of millions of devices are running Linux at this very second. LibreOffice, GIMP, and Firefox are other examples of open-sourced software. Open-source projects are usually contributed by developers who work on the project for free in their free time. These massive software development efforts were essentially built by a community of volunteers. How great is that? In an IT environment, you'll have to pay special attention to the types of software you use. Some may require you to pay multiple licenses to use it. Others might be free and open source. It's important to check the license agreement of any software before you install it. We've talked about some of the basics of software, but now let's shift to the two types of software you'll encounter, categorized by function. Application software is any software created to fulfill a specific need, like a text editor, web browser, or graphic editor. System software is software used to keep our core system running, like operating system tools and utilities. There's also a type of system software that we haven't defined yet, called firmware. Firmware is software that's permanently stored on a computer component. Can you think of a firmware that we've talked about already? If you thought of the BIOS, you're right. The BIOS helps start up the hardware on your computer and also helps load up your operating system. So it's important that it's in a permanent location. I should also call out software versions. These are important because they tell us what features were added to a specific software iteration. You'll encounter lots of software versions while you work with software. Developers might sometimes use a different standard when distinguishing a version, but in general, the majority of versions follow a sequential numbering trend. You might see something like this: 1.2.5 or 1.3.4. Which of these do you think is the newer version? It's 1.3.4 because it's a larger number than 1.2.5. You can read more about software versioning in the supplemental reading. You'll have to work with all kinds of software. Fortunately, it basically all works the same way. Once you learn how one piece of software works, you'll understand how others might function. We're going to learn how in the next few videos. Remember that in the 1950s, computer scientists used punch cards to store programs? These punch cards represented bits that the CPU would read and then perform a series of instructions based on what the program was. The binary code could have looked like this, and the instructions would be translated to this. Grab some input data from this location in memory, using the input data, do some math, then put some output data into this location in memory. But storing programs on punch cards was a long and tedious task. The programs had to be kept on stacks and stacks of punch cards. Computer scientists needed a better way to send instructions to a machine. But how? Eventually, a language was invented called assembly language that allowed computer scientists to use human-readable instructions assembled into code that the machines could understand. Instead of generating binary code, computer scientists could program using machine instructions, just like this. Take integer from register 1, take integer from register 2, add integer from register 1 and register 2, and output to register 4. This example makes it look like a human could read it. But don't be fooled. Let's take an example of saying something simple like hello world in assembly language. It looks pretty robotic. Don't get me wrong, that's still an improvement over its binary code cousin. But assembly language was still just a thin veil for machine code. It still didn't let computer programmers use real human words to build a program. And a program that was written for a specific CPU could only be run on that CPU or family of CPUs. A program was needed that could run on many types of CPUs. Enter compiled programming languages. A compiled programming language uses human-readable instructions, then sends them through a compiler. The compiler takes the human instructions and compiles them into machine instructions. Admiral Grace Hopper invented this back in 1959 to help make programming easier. Compilers are a key component to programming and helped pave the road that led us to today's modern computing. Thanks to compilers, we can now use something like this. And it would be the same thing as this. Computer scientists have developed hundreds of programming languages in the past couple of decades to try and abstract the different CPU instructions into simpler commands. Along the way, another type of language emerged that was interpreted rather than compiled. Interpreted languages aren't compiled ahead of time. A file that has code written in one of these languages is usually called a script. The script is run by an interpreter, which interprets the code into CPU instructions just in time to run them. You'll learn how to write code using a scripting language later in this program. As an IT support specialist, scripting can help you by harnessing the power of a computer to perform tasks on your behalf, allowing you to solve a problem once and then move on to the next thing. Programming languages are used to create programs that can be run to perform a task or many tasks. There are lots of types of programs, and in the next lesson, we'll talk about how to manage them. Program, software, and applications are terms that are synonymous with each other. For now, we'll go ahead and use the term software to refer to any of these. We've already had a rundown of the different types of software. There are certain types of software that perform specific functions, like drivers, which allow us to interact with our hardware. There are applications that we use for our day-to-day job functions. And there are utilities that we use, like a calculator, settings, and other tools. With the seemingly endless options for software, how do we know which ones to use? How do we deal with them in a workplace setting and in our personal lives? Software is always changing. Developers are releasing updates, software companies change, features are added, and so on. This constant change is completely out of our control, and it can cause a lot of headaches in the IT world. Let's say the company that builds your payroll system pushes out a software update that causes settings to change, or even worse, completely breaks the compatibility with your own company. It can happen. You should always test new software before letting your company use it. Another thing to worry about is old software. When you run old software on your machine, you risk being exposed to cybersecurity attacks that take advantage of software bugs. A software bug is an error in software that causes unexpected results. We'll deep dive into computer security in a later course. For now, know that software updates usually contain critical security updates and new features, and have better compatibility with your system. A good guideline is to update your software constantly. Another problem that plagues the IT world when it comes to software is software management. If you're setting up a computer for someone, you want to make sure that they'll have all the necessary tools they need to hit the ground running. That means you'll need to install all the software required for their job. That may also mean that sometimes you'll want to remove software that isn't required for the job. We may not realize if a piece of software we installed is malicious software, which causes harm to your computer. It's always a good idea to check if software comes from a reputable source before you install it. A common industry practice is to not allow users to install software without administrator approval. This prevents users from installing unwanted software because they're actually blocked with an error message that says they need an administrator to enter their login credentials. Before we get too far ahead of ourselves, let's cover the basics of software management, which include installing, updating, and removing software. In the videos up next, we're going to walk through how to do these steps in a Windows environment and a Linux environment. Ready, set, go. Get ready, because in this video, we're going to install a program called Git. Git is a version control system that helps keep track of changes made to files and directories, like how some word processors today have a revision history feature. If you didn't like something you wrote, you can just go back to a previous version. First, we're going to grab the install program from Git's website. We're going to download the 64-bit executable. Remember from an earlier lesson that we're using a 64-bit CPU architecture, so we should install 64-bit applications for better compatibility. Next up, you'll see the file extension .exe. This is a little different than the text or image file extensions we've seen up until now. .exe is a file extension found in Windows for an executable file. We'll learn more about this in a later lesson too. For now, just double-click on this, and it'll ask us if we want to install the file. Voila, that's it. Now you can start using it. Some program installations might ask you to reboot. Make sure to do that, since there might be some system files or processes that also need to restart for your new software to work correctly. To verify that you now have Git installed, you can navigate to Add or Remove Programs. From here, you can see what applications are installed on the machine. And there it is. Git version 2.14.1. Let's say you had an older version of Git installed and you wanted to update it to the new version. Luckily, Windows makes it easy for us to do just that. We can install it just like we did, and it'll ask if we want to upgrade to the newest version. To remove software from Windows, you can just search for the Add or Remove Programs setting. From there, select the application you want to remove, and you'll see a button to uninstall. Let's go ahead and click this and run through an uninstall of the software. It asks us for an administrator password. We have safety guards in place to prevent unauthorized users from installing or uninstalling software. We'll learn more about this later, but for now, since I'm an administrator, I'm just going to enter my password and uninstall the software. Once you uninstall software, restart your computer so we can do the necessary cleanup to completely get rid of it. You're doing awesome. By now, you've learned what software is, how it integrates with our computer, and how we manage it. It was easy to install, update, and remove software on one machine. But what if you had to do that for multiple machines? That would take up a lot of time. If only there was a way we could have it done automatically for us. Spoiler alert, there is. We use software to help us with this. There are lots of tools out there that help make managing computers easier. We use automation for this. Automation makes processes work automatically. You can even use the tools of automation like programs and scripts to help you with troubleshooting issues. So instead of reading hundreds of lines of log files manually to discover when a particular error occurred on a computer, you could write a script to read the log for you and print out only the relevant line. Software has many uses, including making processes more efficient and easier. You made it all the way through software. Nice work. Next, you'll meet Marty Clark. She's your instructor for troubleshooting, and will talk to you about how good customer service is critical to IT support. In the meantime, work hard, soak up a ton of knowledge, and have some fun along the way.
You've already learned about the hardware, operating systems, and software layers of the computer architecture model. Now it's time to learn about the most important layer, the user layer. Troubleshooting problems and solid communication with users may be one of the most challenging parts of your job as an IT support specialist. But by the end of this module, you'll know the best way to handle them. Fixing problems and creating positive interactions with people are two fundamental skills that can be applied to almost any situation in the IT world and beyond.
Bye, Wendy.
Knowing how to analyze an issue, identifying the causes and effects, and use the information to find potential solutions are skills that everyone from IT support specialists to doctors can use. Hi, I'm Marty Clark, and I'm a manager with Google's internal IT support program. Even though I grew up around technology and worked at my university's help desk, going into tech wasn't something that was encouraged by my teachers or my family. Now, as a manager, I try to encourage all techs I work with to follow their passion. It's this passion to help others grow and my love for technology that led me here. Helping people with technology is both a rewarding and challenging endeavor. I encourage my team to take advantage of their work with users to spin up ideas, solutions, and opportunities for improvement. The technical aspects of problem solving are super useful, but don't forget the real reason most technology exists is to improve people's lives. Whether it's the routing algorithm that formed the backbone of the internet or the software tools that let people create amazing art, the ways that people interact with technology are central to IT. As an IT support specialist, you're uniquely positioned to combine technology and people know-how to make those interactions better and make a difference in people's day-to-day lives. How would you respond if I asked you, do you know how long it'll take me to get to the bank? You'd probably ask, where are you? Where's the bank? Are you walking, driving, biking? But if you just guessed the details of my situation to direct me to the bank, your response would be a day late and $1 short. It seems like such a natural thing to ask questions and gather information to solve a problem, but it's usually one of those most overlooked steps in troubleshooting. Troubleshooting is the ability to diagnose and resolve a problem. One of the most difficult skills to acquire in an IT role isn't technical knowledge, but effective troubleshooting, whether that's helping someone face-to-face or remotely. It's not specific to the IT world either. We use troubleshooting skills every day. My car is broken. The light bulb went out. I feel sick. Imagine if you went to your doctor and said, I feel sick, and without any other information, he gives you a prescription for allergy medicine. Time to find a new doctor. While this might seem far-fetched, this can happen pretty often in the IT world. We're so in the habit of fixing things that sometimes we try to fix something without diagnosing it first. We're going to give you the tools you need to develop good troubleshooting habits. No matter how big or small the problem is, the first thing to do in troubleshooting is ask questions. There are a lot of factors that can cause a problem. You want to make sure you gather all your data before you start to tinker with it. Over the next several videos, we're going to demonstrate real-world, in-person, and remote troubleshooting scenarios. For the in-person scenarios, you'll meet Gail and Marty. And yes, we have another Marty joining us. But he spells his name with a Y, and I spell mine with an I. Confusing, I know. Please keep in mind these are not professional actors. We want to give you the opportunity to see how these different scenarios would play out in real-world settings. Let's look at a quick scenario of a not-so-awesome troubleshooting interaction and an awesome one.
My computer's broken.
Ooh, this looks bad. I think you're gonna need a new computer. It's gonna be about $1,000.
My computer's broken.
Ooh, okay. Can you tell me a little bit more about how it's broken? Does it turn on at all? Has there been any damage to it lately that you know of?
Well, when I hit the power button, I hear a ding, but nothing comes up on screen.
Oh, okay. Can I take a look? Sure. Okay, let me just see what's going on here. You know what? The brightness was turned down. These brightness buttons are a little bit fiddly, and it's easy to hit them by accident. So there you are.
Great, thank you.
You're welcome.
If we didn't ask follow-up questions, we wouldn't have realized the issue was something as small as the screen being dim. So it's important that you're able to gather enough information to start troubleshooting an issue, whether it's big or small. With a little digging, we were able to understand the situation and effectively troubleshoot the issue. What's also really important to call out from this scenario is the tech didn't make the user feel silly for not realizing the screen's brightness was down. Can you think about a time someone made you feel silly or even dumb? It's a pretty terrible feeling. So don't be that person that does it to someone else. Remember, IT support is about working in the service of others. Always try to create a positive experience for the user. We'll deep dive into customer service later on. In the meantime, I'll see you back in the next video on isolating the problem. Now that we have the ask questions approach nailed down, let's cover another effective troubleshooting method, isolating the problem. The goal of this method is to shrink the scope of the potential issue. Let's start with a simple game. I have a number I'm thinking of that's less than 100. Can you figure out what it is? You have 5 questions you can ask me. As you might have guessed, just guessing a number isn't the way to go. Is it 5? No. Is it 7? No. Your odds of figuring it out this way are super low. Instead, you should be shrinking the scope of where the number could be. So you could ask, is it greater than 50? No. Okay, so we know the number is 50 or less. We've just isolated our problem and cut down half of the answers we started with. To narrow the scope further, you could ask, is it greater than 25? Yes. Is it greater than 38? Yes. Is it lower than 45? Yes. Is the number 42? Yes, the number is 42. Nice work. The power of isolating a problem can quickly and effectively help you figure out where the issue lies. The isolate the problem method is meant to shrink the scope of your problem so that you know you're looking in the right area. After you continually isolate the problem, you'll eventually end up at the root cause. Root cause is the main factor that's causing a range of issues. Finding root cause is a critical concept in IT support because it means that you're able to prevent an issue from happening again and again to multiple users. Sometimes the root cause can be difficult to find and extremely obscure. Don't give up if it isn't immediately obvious. Discovering root cause may be tedious, but it's well worth the effort. Now let's take a look at a not so good and a good example of isolating the problem.
Hi, Marty. I can't get my email to work on my laptop.
Hi, Gail. I'd be happy to help with that. Somebody came in the other day with the same problem. Let's uninstall and reinstall the application.
It still doesn't work. Hey, Marty. I can't get my email to work on my laptop.
Oh, hey, Gail. Sure. I'd love to take a look at that. Have you tried checking your mail on your phone or tablet or something like that?
No, it doesn't look like that's working either.
Ooh, let me try. Wow, you know, I can't get in either. Let me look into this for a sec. It appears that the email server is down. The notice says that it's going to be down for about another hour. How about we wait an hour, try again, and if you're still having a problem, we can dig deeper.
Okay. Thanks, Marty.
You're welcome, kiddo.
As you can see, it's vital to use the isolating the problem method to decrease the scope of the issue. If you can rule out a problem area to look at, you can troubleshoot more efficiently. Another effective troubleshooting method is called follow the cookie crumbs. What purpose does this serve besides making me want to devour a cookie? Well, this method requires you to go back when the problem first started and work forward from there. You'd be surprised how much information you can learn from asking, when did this problem start?
Can you help me with my phone? My FunCat app stopped working.
Sure. Now, what do you mean by stopped working?
Well, when I tap on the app, it starts to load and then it crashes.
Well, take a look here. Okay, let's try reinstalling the app and see if that helps.
It still crashes. I need my FunCat app. Can you help me with my phone? My FunCat app stopped working.
Sure, I'd be happy to. Can you tell me a little bit more about how it stopped working?
Well, when I tap on the app, it starts and it just crashes.
Ooh, that's not good. When did it start? Have you changed anything since that time?
Well, it worked last night, and I was playing around with it until it started to update, and this morning it just didn't work.
You know, it might have something to do with the update. Let me take a look into it. Okay, looks like there was a bug in the update. We can roll back to an earlier version and see if that helps.
Oh, Cuddly and Peanut, I missed you.
The user can give you information about what they remember, but the systems you work with can also offer insightful information. In the earlier lessons about operating systems, we talked about logs. Remember that logs are like your system's diary. They keep information about dates and events that happened on the system. You can dig through logs at the exact time that a failure happened, and you may find some defining events that could have caused your issue. We'll get into logs in more detail in another course. Error messages are super helpful indicators that can point you in the right direction. Lots of times, a single error will be lost in a sea of errors. It's best to start from the very first error, which may be causing a cascade of errors. By fixing the root error, you'll correct all the other ones in the process. Some errors don't require extra digging, like a 404 not found error you might see on websites that have been moved or deleted, or a permission denied error when accessing a protected file. Let's take a look at this log. I see an error message here at the bottom. Do you think it makes sense to try and figure out this error message and resolve it? You might find yourself spending all day trying to fix these little holes. Let's backtrack up the log a bit instead. Oh, look, we can see where an error first occurred. Let's try to fix this. And now our system isn't yelling at us anymore. We've asked some great questions to understand our problem. We've isolated our problem to an effective area and looked at our cookie crumbs. Now it's time to start fixing the issue. In the IT world, as in life, problems don't always have one right answer. When you troubleshoot an issue, you're essentially trying to isolate it to the root cause. To help you isolate an issue, you need to try some remediation steps. If they don't work, then you can rule those out as the cause. So what's next? Here's where the start with the quickest step first method comes into play. We want to get to our root cause effectively, but sometimes there are multiple options we can use to isolate something. So how do we know which option to try first? It's pretty simple. Try whatever's fastest first.
I'm having a really weird issue with my software. When I start it, it doesn't do anything, and I just installed it.
Interesting. You know, it might have gotten corrupted during installation. Let's reinstall it again.
It still does the same thing. I'm having a really weird issue with my software. When I start it, it doesn't do anything. And I just installed it.
Do you happen to remember if you restarted the computer when you installed it?
Oh, it works now.
It's possible that in this scenario, a software reinstall could fix the issue. It's also possible that a restart was the solution. Since you can test a restart faster than a reinstall, you should test the restart first. You want to be able to troubleshoot and resolve issues effectively and efficiently. So remember to start with the quickest step first. Your time and your user's time are important. You've gained a lot of great foundational troubleshooting skills, but there are some common pitfalls that you should try to avoid in order to be at the top of your troubleshooting game. As an IT support specialist, you'll sometimes encounter the same issue over and over again. Before the next issue comes in, you may find yourself using your muscle memory to fix the issue. Pitfall number 1, going into autopilot. Make sure you don't default to autopilot mode, moving through issues out of habit and without careful thought. More often than not, there are small variables that change the problem you're seeing entirely. Ask questions and gather data so you can fully understand an issue. This takes less time than having to redo some sloppy work you did in autopilot mode. Pitfall number 2, not finding the root cause. It's very easy to get distracted by small problems that pop up, but it's super important to remember there's probably a very big problem causing all these small problems. Spend a little extra time investigating the issue instead of trying to fix all the small holes. If you're trying to do a quick fix, it's tempting to wipe a system and start from scratch. This approach is kind of like using a hammer when a surgical scalpel might be a more appropriate tool. Let's say a user isn't able to access a particular website. Re-imaging the system isn't a great solve. It doesn't get to the root cause, and it doesn't help further your own knowledge. Investigating the problem a bit, testing out possible issues and solutions incrementally, and identifying the root cause can end up saving a lot of time and effort in the end, and it feels really empowering as an IT support specialist. And with that, you'll be able to go out in the real world and use your new skills to methodically troubleshoot an issue. Customer service is a critical skill in IT support. I can't emphasize that enough. You can have all the technical knowledge in the world, but if the user had a poor experience in the process of getting their issue solved, you failed. The techniques we'll discuss in these videos won't only help you with your users. They'll help you work better with your peers, your managers, and maybe even your own personal relationships. Keep in mind, these techniques don't work in all situations. The reality is that no matter how great you are at customer service, some situations don't have a good resolution. Plus, everyone is different, so you'll need to tweak your style when working with users. But the techniques we'll cover are intended to make your IT interactions more successful. In IT support, you work with users to fix technology and improve how people use it. To accomplish this, you need to develop a trust between you and the user. Lots of employers believe that good customer service also builds brand loyalty, which is a key to success. These lessons are meant to give you the foundational skills and techniques of how to deliver great customer service. Customer service practices can differ from company to company, so while we'll cover the key concepts of customer service in any IT support role, it's important to talk with your employer to understand the company's customer service approach. This will also give you an idea of how much freedom or restrictions you might have in the role. Spoiler alert, great customer service requires exhibiting empathy, being conscious of your tone, acknowledging the person you're talking to, and developing trust with the user. If you remember nothing else from this lesson, remember those 4 things. The most important of all of these is empathy. What's the difference between sympathy and empathy? People will say things like, sympathy is saying you're sorry, empathy is feeling sorry. That doesn't really explain it. So let's use an example to drive this home. If someone fell into a dark, damp, dirty hole, and you leaned over with a sad expression and said, "That must be a really tough situation," then you're expressing sympathy. You're sharing their feelings, but you aren't experiencing those feelings. If you crawled down into that dark, damp, dirty hole with the person who fell and said, "This is a really tough situation," then you're expressing empathy. You're able to see something from someone else's perspective and understand their feelings. The word choice between the 2 situations is very similar, but the action you take by looking at it from their perspective is what empathy is all about. Some days it's hard to empathize. I know from experience. Maybe you had an argument with a loved one before work. Then by the end of the day, you find yourself getting annoyed or upset with users. That's the moment when empathy becomes the most important, because anyone can showcase empathy when it's easy, but someone who persistently displays empathy will stand out as a kinder human and a more professional and effective employee. Once you have empathy down, you should think of your tone. Tone is historically thought of as how you speak out loud. In this technological age, when many of our interactions are over text and IT support is increasingly done remotely, tone isn't just about how you come off during an in-person conversation. It's expanded into how you write, punctuate, and even spell. If your tone is short or blunt, then the user will feel brushed off and devalued. But if your tone is friendly and curious, the user is much more likely to have a positive experience working with you. Be careful not to go overboard with the friendliness, though. It could be disingenuous. Communicating a good tone is a delicate balance. How you ask a question and how you respond to a user's question matters. Let's say you tell a user in an email, "Turn your computer off and on again and it will start working." They'll probably never respond, and your company may have lost a customer because the tone is just too short and pretty unfriendly. While it gets to the point, it doesn't leave the door open to a conversation. What if instead you wrote, "Please try turning your computer off and back on again. This should update the change we made and fix the problem. If that doesn't work, just let me know." It's a little wordier, but it has a better tone of asking versus telling. Inviting them back to connect with you in case the issue isn't resolved leaves the lines of communication open. Tone can be especially difficult when you're supporting someone in a different region or country. Make sure to familiarize yourself with the local style, whether that's more conversational or direct, and adjust your style depending on the audience. In this day and age of text and email, it's easy to ignore what someone says. If a comment seems like a dig or it's just too much information provided, we tend to shy away from responding. It's also really common to forget to tell the user what you're doing while you're troubleshooting. That might leave the user waiting in an awkward silence. Whenever possible, acknowledge the user. This reduces the tension that might build and helps you understand how you're working toward a solution. Let's say you're chatting back and forth with a user. You're asking a lot of questions to better troubleshoot the issue. The user is answering them, but also makes comments like, "Geez, I already answered these in my last email," or "I just want to know what's causing my problem." You choose to ignore this and continue on with your troubleshooting. You think you're close to solving the problem, and these side comments are just a distraction. But then the user stops fully engaging with you and only gives you half answers to your questions. Now you're not able to solve the issue at all. The user's unhappy, you're unhappy, and the company's unhappy. It's a bad situation. Instead of ignoring the user in that situation, you could have said, "I'm sorry for asking these questions. Sometimes repeating them will help new information pop up." Or you could have said, "Sorry for the repeat questions. I don't want to give you a superficial cause when we could fix the root issue and you won't have to chat with us again." This helps them to understand your method and become part of the solution. It's important to acknowledge your own actions if you think they might otherwise confuse the user. Let's say a user contacts you to fix something. After collecting some information, you go radio silent. What's the user to do? Would they ask if you're still there? Would they wait awkwardly until you came back on the line? How long would they wait before ending the call or saying something? How would they feel about their interaction with you? Pretty awkward. But what if you said, I need to do some research on this issue. Would you mind waiting about 5 minutes or less while I do that? They'd probably say sure and keep themselves occupied while they wait. They'd also feel more confident in your ability to resolve the issue. This leads to the most important thing to remember when working with people, and that's developing trust. This is easy to do if you have repeat users. They see you every workday. One bad day isn't going to stop them from trusting that you know what you're doing. But in a transactional user base, where the user only contacts the company once or twice, how you interact with each user each time is going to break or build that trust. Why is trust so important? Without it, the user could be difficult to work with and could even ignore your advice completely. Empathy and acknowledgement are a big part of building trust. Without these, you'll find it difficult to connect with the user. By seeing things from the user's perspective, you're more likely to find the solution that will help them specifically. This lets them know that you care, and they'll be more likely to be engaged in the interaction. It's also important to follow through on your commitments and promises. If you tell someone you're going to follow up in 1 hour, then be sure to make it happen. And if you don't, acknowledge the oversight and apologize. Be sure that any claims you make can be backed up. Don't make something up to a user because you think it'll help in the moment. Be honest with the user, even if you think they won't be happy about it. And never be afraid to admit when you're wrong. This might be the hardest thing to do with a user, but you'll find that your interactions are more successful this way. Being specific and empathetic with your apologies will give it more meaning. And remember, no one wakes up in the morning thinking, I'm gonna be a jerk today. While you shouldn't sacrifice your self-respect, do your best to give the user the benefit of the doubt whenever possible. Now that we've covered the main customer service techniques, we're going to dive into some of the nitty-gritty by looking at the anatomy of an interaction. These apply to any channel of IT support: email, phone, chat, or in-person interactions. From the first moment you interact with someone, it's important to think about how you say hello. Do you make sure to tell them your name? Do you incorporate information you know about them in your greeting? Do you ensure a positive tone? Are your spelling and grammar on point? These are all ways to create a really good start to the interaction. Some of these things are hard to achieve though. I'm a horrible speller, especially when I'm in a hurry. But knowing some of these trouble spots ahead of time will let you find ways to address them before the interaction. For me, I know that when I'm in a hurry, I need to recheck my spelling before hitting send. Have you ever heard the phrase, first impressions last a lifetime? Well, that might be a bit of an exaggeration. It touches on some truth. How you first interact with someone will influence how the rest of the interaction plays out. I'm not saying you have to be over the top, gushy, and nice. That might have the opposite effect. Just be professional, acknowledge the user, and show them some respect. Taking the time to get the interaction off to a good start will make everything that comes after easier. Let's check out 2 scenarios to see how this plays out.
Hi, Gail. How are you doing?
Not great. It's been a bad day trying to get my phone fixed.
Oh, what's wrong with your phone? Hi, Gail. How are you today?
Not great. It's been a bad day trying to get my phone fixed.
Oh, sorry to hear that. Let's see what we can do to turn that around.
Just by acknowledging their feelings and demonstrate your desire to help them, you've started to build a relationship with the user. Of course, you have to keep up the good work throughout the interaction, but laying the groundwork is an important first step. And remember that while you might have 100 issues in the ticket queue that need your attention, this is the only one that matters to the user. So show them it's your priority too. The next critical step in an interaction is how you respond to the user's questions. If they're taking the time to explain to you what happened, but you brush off their concerns by acting uninterested, things are going to go south fast. Remember to integrate the information you've been given into your conversation. This will show you're actively listening and can help them feel more connected to the interaction. Let's look at an example. Which one of these greetings do you think is the most effective? Greeting 1. Hi, Rory, how are you today? What can I help you with? Or greeting number 2. Hi, Rory, I hope you're having a good day despite your computer randomly turning off. Let's see what we can do to fix your issue. It's important to be transparent with the user. If they start asking you a bunch of questions while you're still troubleshooting, you can do 2 things. First option, you can ignore them because they're just talking out loud. Second option, you can pause and say something like, I'd be happy to answer all of your questions, but I want to look up this one first. I've written them all down though, so I won't forget them. If you say that, make sure to write the questions down. To really build a rapport, try to remember a personal fact they've mentioned and bring it up later. Maybe they mentioned they love cats. Later, while you're waiting for something to load, ask them if they have any cats or what their cat's name is. This shouldn't be forced, so if you're not the type to engage in small talk, skip it. Now you're getting to the point where you're ready to troubleshoot. Just make sure you clarify the person's issue before you start to troubleshoot. If you don't, you might find yourself going down a rabbit hole. Imagine that a user tells you their computer can't get online. So you look at the IP address, DNS configuration, and you start pinging things with no luck. Everything seems fine. Then, 20 minutes later, you find out their machine is online. They just can't access a particular page. Had you clarified this at the start, you would have saved yourself and the user 20 minutes. It seems simple to clarify the problem space, but it's often overlooked. Take this example.
Thank you for calling. This is Leon. How can I help you?
Hi, Leon. My computer isn't working.
That doesn't sound fun. What do you mean by the computer isn't working?
It won't connect to the internet.
Do you have the corporate password for the Wi-Fi?
No, why do I need that?
In order to connect to the Wi-Fi in the building, you need to use the corporate password.
Well, I'm not in the building. I'm at a cafe.
That's odd. Your computer seems to be different than what we normally use. Can I get your name so I can look up your configuration?
Ling Chan.
Do you work at this company?
No, my friend gave me the number.
Problem solving is a super important aspect of an IT support interaction. Being an IT support specialist means that you could be asked about anything. Even though you aren't expected to know the answer off the top of your head, you should know where to start looking to find it. People are coming to you because they have a problem they can't fix themselves. Sometimes they feel self-conscious about asking for help, so be aware of how you probe for information. Pummeling the user with question after question will probably create frustration on both sides. Make sure to set context and explain why you're asking the question. Saying something simple like, in order for me to figure out what's really going on, I need to ask you some question, can make all the difference. When you're in person, things are a lot easier because you can see each other and read each other's expressions, but you might find yourself too comfortable. Imagine you're asking for help with your phone. You wouldn't want the person helping you to just take it out of your hands without asking. So make sure you tell the user what you're doing before you do it. If you're supporting a user remotely and need them to run some commands, don't forget to tell them why you need them to execute the commands. There's no need to go into a ton of detail, but without some context, you could strain the trust you've built. Make sure that when you're asking these questions or asking the user to run a command, you're really listening to the response. Those little nuggets of information may help solve the issue. The last 5 minutes of the interaction will set the tone for how the user feels walking away from the interaction. So make sure to end on a positive note. You might have solved their issue, but if they don't feel it was resolved or they're unsure of the next steps, then they're going to walk away feeling like it was a poor solution. So how do you make a good final impression? Simple. Reiterate the resolution, state the next steps, then ask the user if they have any questions. If you've ever worked in customer service, then you've dealt with difficult situations. The way you handle them in the food industry and tech world are pretty similar. But before we dive into that, we're going to take a step back and talk about the science behind what's happening in these situations. Let's say someone's yelling at you. Whether it's about an overcooked steak or a broken computer, your reaction to either will probably be similar. Your palms might be sweating, your hands might shake, or your mouth goes dry. Tunnel vision might kick in. These are all normal physiological reactions that happen in response to a perceived threat. This is part of our biological make dating back to the time when people hunted for their food. When you're being chased by a cougar, you needed your senses to be at high alert in order to keep yourself alive. Even though someone yelling at you isn't the same as the cougar attacking you, it can feel similar in the moment. Your brain is releasing a mix of chemicals and hormones to heighten your senses and keep you alert. Unfortunately, a side effect is that you may have trouble focusing on a specific task. Not ideal. It's in times like these that you might go on autopilot, where your body has a physical reaction and it's hard to focus. It's super important to recognize these moments and put a plan in place to reboot yourself out of the situation. Sometimes I feel this way when I'm teaching a class and someone is ignoring me. They just don't pay attention. I used to call them out on it, the fight response, but this never ended well. Sometimes they had a good reason for being on their phone, and calling them out never made them listen more. Now, when I feel myself in that situation, I notice that my pulse increases. When I realize that's happening, I make sure to look around and focus on people who are more engaged in the lesson and make eye contact with them. Soon, I feel my pulse slow down. Some of your experiences in IT support might trigger similar reactions. Once you've identified this reboot action, write it down. Remember, your brain isn't always working well in the heat of the moment, so it helps to have something to remind you what to do. It could be anything from squeezing a stress ball to looking away to taking a deep breath. The first couple of times, it may not work, so give it time. When you have a difficult situation, take a moment to think about what went wrong. How are you feeling? What was your reaction? Why did you raise your voice? After a while, it becomes second nature to catch yourself and de-escalate the situation. To really hold yourself accountable, tell a coworker what you're trying to do. Give them a recap of the interaction and ask them for their feedback on the interaction. You might get some great tips. But here's the bad news. Things aren't over once you get yourself back on track. That's when the hard work starts. Every situation is different, and you'll learn the best strategies from experience and peer feedback. To get you started, I'll run through some tried and true techniques. Keep in mind that it's fine if you don't get these right the first time. It takes practice, reflection, and feedback to really nail it, so don't give up. The hardest and arguably the best technique is to identify where the interaction went wrong in the moment and redirect the conversation. This is really tough because it means remaining calm enough to objectively look at the interaction and understand what could have caused it to escalate. At first, try this once the interaction is over. You start your chat with the user, and it's really pleasant and problem solving is happening. Then suddenly the tone turns dark. What caused it? Where was the misstep? Looking back, you might notice that the user didn't understand the question about what happens when he tries to sync his phone. And the tech just kept repeating it. The user gets annoyed and then starts typing in all caps, a clear sign they're irritated. In this case, the cause seems obvious. If the user didn't understand the question, then they probably got frustrated when the same question was asked over and over. If the IT support specialist had noticed this, they could have reframed the question and broken it down further. Another cause of frustration in user support interactions is when people talk over each other. This usually happens over the phone, since there's sometimes a delay, but it can happen in person too. Typically, it leads to people talking louder and sometimes ends up feeling like you're yelling at each other. You've probably been in a situation like this with your friends or family. Everyone wants to talk, and the person with the loudest voice wins.
How can I help you today?
My laptop isn't working. I need a new one. I have meetings I need to go to.
I can certainly look into this and see what we can do to fix it. But I want to set context that our policy is to only replace laptops if all other options have been exhausted.
I don't need you to go snooping around my computer. Just give me a new one.
Gail, I'd love to do that for you, but...
That's ridiculous. I'm a director. I should get a new one. I don't have time for this.
I completely understand the urgency of the situation. Why don't you let me take a look at it?
That's why I came. You need to fix it.
It's important to try and identify why this is happening so you can course correct. In this case, you can simply stop talking to calm things down. Then pause for about 5 or 10 seconds to make sure they're done talking and start again. This might take a few tries before the user realizes what they're doing and gives you time to talk. Use that time to calm down and really listen to what the user is saying. Ask yourself, why are they talking over me? What am I missing? Then in those 5 to 10 seconds, collect yourself and think about what you want to say.
How can I help you today?
My laptop isn't working. I need a new one. I have meetings I need to go to.
I can certainly look into this and see what we can do to fix it. But I want to set context that our policy is to only replace laptops if all other options have been exhausted.
I don't need you to go snooping around my computer. Just give me a new one.
Gail, I'd love to do that for you, but
That's ridiculous. I'm a director. I should be able to get a new laptop. I have no time for this.
I completely understand. Can you let me have 5 minutes to do a quick triage and then we can discuss next steps?
If the user is crossing a line and making you feel uncomfortable, ignoring it can feel like the easiest solution. It isn't. Remember that if you do, the next person they interact with will be treated the same way, and that's not okay. It's also easy to say that the person being attacked needs to stand up for themselves. But in situations like this one, that's really hard. Ideally, bystanders would call out this behavior in a calm way. It's also important that you escalate these issues to the appropriate channel, whether that's your manager, the human resources department, whomever. Disclaimer, I love being in the IT support field, and I don't want to dwell on the negative, but I do want to prepare you for what you might encounter. So let me throw another tough scenario at you. You might find that a user skims over what you wrote or doesn't listen to the full instructions you present before taking action. When this happens, be patient. You've likely been on the other end of this before when you ignored instructions. Why? Were you overwhelmed with the information? Were you in a hurry? Maybe you need reading glasses. Whatever the case might be, the best tactic is to break these steps down into smaller, more digestible pieces for the user. If you sent them an article that they didn't finish reading, ask where specifically in the documentation they're having issues, so that you don't have to bore them with the parts they already know. Sometimes you'll come across someone wanting to bend a policy or push back on an established process. Take this as a sign to look deeper into the situation. Is it really a company policy or just a common way of doing things? If it is a policy, is there documentation of it? You can reference that to the user. If not, offer to follow up to get a definitive answer. You might be surprised what you find. The takeaway here is that it's important to try to see things from other people's point of view. In that moment, when you're feeling riled up and frustrated, take a minute to see the situation from the other person's perspective. If you were them, how would you be feeling? What would make you feel better? If you can train yourself to see things from another's perspective, you're on your way to turning things around.